เราจะไม่มีบอกว่าเข้าไปper esempio, ho un centro con il ciliare unghie, avevamo una e poi vediamo il messaggio You guys can help redirect the people who are coming here to try to take them. So yeah. I'm starting to use you guys though, but we you know the presenters me, I'm going. Why is this how it's lagging? Oh, the senior, the new, principal class, the new principal class, no, no,
I'm back.
okay.
Yeah, principal.
Yeah, next year, yeah, maybe next year.
Next year.
I'm saying for you, next year, yeah, I'm going my video.
Oh,
Someone's over for me interview. I do. Till be uncle in denying.
mhm. Yeah. Ọmọ ẹ̀kìtì pàṣẹ
So yeah, we've been college after. Yeah, and there are the limbo. Madam for the corporate, on no administrator, on no finance for. Then I reflect in part of on the early this year. You know that they are small boys. We need
this year ban mi na. This year ban mi.
a higher progression in finance. I just feel more for and you do cheap for money in that. I hope you know how to share slide. So when the person comes, so this is share, right? So you share the entire screen, not and you just share the entire screen. Then the right and one note, the person is to write notes, right? This one. But meanings are question power to be asked all of them. I thought that was
Why?
Yeah.
Is it? It's
There's Yeah, yeah. Oh,
Probably the one.
draw. Have to go.
Probably this.
But the person imported, so you just create a new one. Mm. Which no.
Good morning. Just want to say, everybody who wants to hear the listen to the lecture today, you must come in front because I have to write on that board. I want to show you some mathematical stuff. I can't do it on the small screen. It's like it doesn't help. This is just a screen for businessmen, not for science. And everybody see this board. And the people in the camera see the board. Perfect. Okay, so today, I want to talk about measurements. All right. We first will maybe finish the thing that we did last time. You know, last time we talked about the impossible machines. And now we also have to talk about possible machines so that we know what to do. Would be very strange if I just talk about impossible machines, right? And it would mean to just learn what you have done, what you shouldn't do. I need a microphone. Where's the microphone? Where is this microphone? Let me alone. Sorry. Okay, so I hope you're ready and you can hear me. If not, tell me. But we have now 2 hours and later 2 hours. So today, these 2 hours, mainly measurements, later communicate in the last 2 hours, right? And I want to do it a little bit hands-on. So means I'm gonna write things down. So possible machines, okay? Not sure if this is the right answer. Okay, so better take notes, always good to take notes. Then you can already process what is going on. And what I said here is a possible machine, so QIP, which is quantum information processing. And in brackets, I said QT, which is quantum technology. So quantum technology, all the machines are, of course, quantum technology machines. But quantum information processing enables this whole thing. So it's all about information. It's a very strange change that in physics, or at least in this quantum technology, we talk about information. You know, why do we do that? Seems to be a new way of looking at the world, you know. And sometimes that's good because then you get new ideas. If you look from a different angle, doesn't mean that you cannot find another way of describing the world, you know. But what we do here, at least in this lecture, is now from the viewpoint of information. Okay, so last time, so the first thing I want to talk about is quantum cryptography. Who knows what cryptography means? Cryptography. Do you know what that means, cryptography? Yes. Yeah, thank you. Did you hear? So ways of encrypting data so that it cannot be misused. All right, that's cryptography. And what is the big advantage of quantum cryptography? Well, the big advantage is that we have no cloning. Okay, so if I have a sender, and the sender sends a classical signal to receiver, okay, then I can always put in a copying machine that gives the signal also to a eavesdropper. Okay, so this is the eavesdropper. And of course, if it's now encrypted, then he can't read it necessarily. But as I told you last time, most encryption schemes that we currently have, at least those that are asymmetric encryption schemes, so that work with a public key, they are based on mathematical complexity, and it is believed that most of them can be cracked once we have a quantum computer. So in 5 or 10 years, at the so-called, they call it the Q day, you know, there will be a lot of data that it can be decrypted using a quantum computer. And what people do, goodbye. See you in 10 years. So, it can be decrypted, you know, only in 10 years with the quantum computer. And what people do is harvest now, decrypt later. Okay, so I just harvest the data now. I eavesdrop on it. I can copy classical data, no problem. Right? And then later I decrypt it once I have the quantum computer. Right? So that is a real danger. It's really, this is already kind of known. And this is what we do harvest now, decrypt later. Okay, so harvest now, decrypt later. So now, what do we know in terms of quantum signals? So if I send a quantum signal, we always write these quantum signals with curvy lines, you know, to a receiver. Then we know that such a machine does not exist. Okay, does not exist. So no, there is a no cloning theorem. And I highly recommend that you actually look for that. There is a Nature article of 1982 by Butas and Zurek. Wojciech Zurek. With Butas and Wojciech Zurek, some heroes of quantum technology, I would say, or at least foundations of quantum technology, quantum mechanics. And they wrote this article about the no cloning theorem. If you Google it, I can tell me, I can give you the reference, I have it here somewhere. This is a very nice article to read. And it's only one page, you know, and it's like, you don't need to write more than one page if you if you want to do these things. One interesting question by the referee that looked at this article was apparently what happens in a laser. You know, in a laser, you have stimulated emission, and that emission is stimulated by putting some photons in the right state, okay, into a cavity. And then there are atoms that emit photons, preferably into this same channel, you know, with the same direction, with the same spatial mode. Okay, so basically you are copying, you're cloning a photon, the state of a photon. So the referee wanted to know how can you reconcile that with your no cloning theorem? You know lasers exist, right? And the trick is, it is true that lasers exist, but there is always noise in a laser. Namely, if you have always a process called spontaneous emission, where the atom spontaneously hops down, and then the photon can go in all directions. So the fidelity of copying or of cloning is limited. And it turns out that the higher the photon number is, so if I want to go from n to m photons, where n is a very high number already, then it becomes easier. The relative noise becomes less. Right? The relative noise becomes less. So it gets better if you have more photons. But if you want to copy if you have a single copy, you want to make another copy, then it's really bad. You know, it's actually, we will calculate how bad it is. The fidelity is 2/3. You cannot get higher than that. No, 4/5, sorry. Okay, we'll see later, right? 4/5. And so this doesn't really exist. It's not possible to perfectly clone. And read this article, very interesting article. And therefore, because we cannot copy quantum information, we can now actually send the information on the quantum channel without that we have to encrypt, in principle, because no one can copy. No one can see what we are sending. But there are kind of nice schemes that put in a little bit more security than just sending blank photons. And we will see that later. Okay. So this is one of the machines that works. It's sending information over quantum channel, and it will be a sequence of zeros at once. And we'll discuss it in this afternoon. And then you will see that this sequence of zeros and ones can be used as a key to encrypt classical messages, and then send these classical messages over public channel. So I can send you, if we have a quantum channel, say from here, from Durban, where I live in South Africa, to here, if we would have that, then I can send you a key, and you use that key to encrypt your messages, your cell phone messages on WhatsApp. No one can. You can even publish it in a newspaper. No one can understand. Right? So this is what I want you to keep in mind. In Europe, they built already a big loop, and no, actually in Germany, not in Europe. In Germany is part of Europe. In Germany, they built a loop of such a quantum channel that goes around the whole, that connects basically all big German cities. And then they are secure in 5 years' time when the Q day comes. And we should do the same in Africa. And if we master this, then we are experts anyway. And then we can also sell it. And our big advantage, I read it this morning in the newspaper, they don't have enough people in Germany. You know, they said in the article this morning, hey, people can come all on time. I know how difficult it is, but let's come all on time, because it's really, sorry that I say this, But it's really difficult for me if the door opens for 2 minutes, you know, like yesterday it was all 5 seconds. So please don't leave the room if you don't have to. Should all phone calls to later or errands to them, you know, now we are here. Okay, so I wanted to say, I read this morning in a newspaper, in a German newspaper, that they don't expect, the experts don't expect that Germany can start its economic engine again, because at the moment they are a little bit flat, because they don't have enough people. They don't have enough people, okay? So, so they really think they don't have enough youth, you know, that, but people that can work, okay? So here, this is not the case. I mean, we have enough, and we can do this, and we can do it much cheaper, I'm sure. So watch this space, right? This is one. Okay, so the next one, something here. Okay, the next one is quantum teleportation. Yeah, I will talk about that in all lengths this afternoon. Hopefully, hopefully I can convince you that that is very exciting. Okay. But is it loud enough?
Yes.
Is it okay? Good. Okay. Then I just talk over the microphone. But how now I do this better. Okay, I just this is a good exercise. I just look onto this thing, then I write down what I want to write down, and then I look again when I did write down the right stuff. Okay. So let me do this. One hand for the microphone, another hand for the thing, and what I want to write down might surprise you because what we saw yesterday. Is for it's always people always think it's impossible until it's done.
Yes.
All right. So this is the thing. Yesterday, you remember we did a process called classical teleportation. And it worked like this. We have some quantum system that comes in, then we make a measurement, right? And then we send the classical signal to some preparation machine, okay? And then we try to re-prepare the thing and we fail, okay? This is not possible. This is classical teleportation. Now I can show you how we can make this work. That would be a super surprise for everybody that doesn't know it, including the founding fathers of quantum mechanics. If we put here a source for entangled particles, and we put this particle flies into this machine, and this is then not a preparation machine, this becomes a transformation machine. So it transforms the thing here, depending on the signal, on the classical signal from over there. But I also need to send another particle that is highly correlated with this particle to this thing, and here I make a measurement on 2 particles. Okay, and let us assume for a moment those are qubits. Qubits are particles that have a state space with 2 basis states. So a state space is always a vector space, you know, and the simple systems, they have just a 2-dimensional state space, okay? So there are 2 basis vectors, this direction and one in this direction, okay? And that means in a measurement, I can only get distinguished one of 2, I get 2 results basically. right? Either I get the result I project onto the one basis state or onto the other basis. Now, if I have two level systems or two qubits, right? Because now one qubit is coming in here. So one qubit is coming in here, and the other qubit is coming from there. Then how many dimensions does the Hilbert space of these, the state space of these two qubits have? What do you guess? 4. Exactly. 4, right? I couldn't think of any other answer. 3, no, I would say it's not enough. And 5, why now? You know, so 4, right? So this is correct. So what I measure here is I get a measurement result that is a number between, you know, usually people nowadays they write everything in bits. Okay, so it's like 0, 0. That's the number of 0. Okay, or it's 0, 1, or it's 1, 0, or it's 1, 1. I think this is number 1. This is 2. This is 3. Okay, in binary digits. So I send this result, and then this guy does one of 4 transformations, and then he gets the exact state out that came. All right. So this is very fascinating because this system here is always in the same state, independent of what I send in here. And I can transfer the state to here without, so the information that travels from here to there has nothing to do with the state. So in fact, it turns out that all 4 measurement results are equally prominent for any state that comes in. So I really make the state appear in a remote place without that any information carrier carried the information in between. So that's like magic. I mean, I find that very strange, you know, that you can disappear here. And it's very important that after the measurement, no information is left about the system, because otherwise you would have got more than one copy. You know, you start with one copy, now the copy is here. And if something was left of the thing, even if it's only a little bit of information, you would have 1.5 copies or 1.2 copies. And that cannot be, according to no clone. You cannot make copies, you see. So it's really like, although, maybe I should be careful with this. We can make copies, but only with a certain identity. So maybe that was not the real reason, but it is true that this measurement totally destroys the state here. And we can, by transforming the state of this system, we can make the system go appear here, right? The state of the system will appear. So somehow I find that fascinating. Do you have any questions concerning this? I mean, we will really calculate this. You know, this afternoon. This is basically what I want to learn. Right? Okay. Are there any questions now? Yes?
If saying there's no source that is standard, it's not connected to both the 2 machines or the quantum teleport.
If you don't have, thank you for the question. So the question was, do you need necessarily this thing? If I take this away, then it's classical teleportation, and we know it doesn't. Right? So you necessarily need this thing. You need the entanglement. And it's not, you know, this appears here and appears here, but a moment later, because I need to send a classical signal. So the classical signal can only be sent with, at most, with the speed of light. So it's not against special relativity. I cannot make this appear here immediately. I must send some information. If I don't send this information, if the guy measures here, it has nothing to do with this. It's very strange. So only by getting one of these 4 numbers and doing some rotation of the system, sometimes I get back, I recover the information. Yeah, I really like it. And we can think together about interesting applications where we bring this information later. I can tell you what I mean by that. In connection with the twin paradox, Anyone knows the twin paradox? Twin paradox. The twin paradox is like this. You start as you have a brother, right? And let's say your brother is a twin, so it's as old as you are. And then you fly to another planet, let's say, exoplanet, and you return. And when you return, you are much younger than your twin. But in your reference frame, you think from the reference frame of your brother, it worked like this. You flew away and you came back, right?
Yes.
And something happened so that you are now younger than him. But from your reference frame, it will look the other way around. He flew away and came back, and now he is older. But why? If the relativity principle, namely that physics is the same in all reference frames, is valid, then it cannot be that if he flies away, he's older, and if you fly away, you are younger. I mean, how is that possible, right? So this is a paradox. And the solution to the paradox is that it's not equivalent, because the one guy has to stop his rocket and return. But with this teleportation thing, we can maybe play a trick. And so we could make an image of the guy that is flying away and send the image, teleport the image back, okay? And we don't send these numbers, because if we send the numbers, it's like if we have returned. So it's like we took our rocket and flew the numbers back, you know? This we cannot do, but we just bring the numbers later. So he stores the picture of the clock that we sent, and later when we come back, we tell him, look, this is my measurement result. Please check the clock. It will show whether I was younger or whether I was older. And that would be a great thing, but I guess it will not show anything. I mean, sorry, I don't know what I should say, but it's an interesting thing. Okay, so coming back, so quantum teleportation is very important, because it allows us to connect networks, these quantum cryptography networks, without that we need trusted nodes. So it basically allows us to build a quantum repeater, which is one of the parts that we need. Okay, so this is an important thing, important for long distance quantum communication. Quantum communication means you communicate using quantum systems. Okay, so let me come to the next one. The next machine that's possible. Yes.
Reference to the question earlier on asked about the number of channels inside the machine. It was reference to the source. That's now an instance of transmitted source to get measurement. And another one from the measurement to the source. I was thinking, when does that happen? The source also receives.
Yeah, good question. So the question was, you know, somehow this measurement must do something to this part, right? But it must also do something to this part of it, because otherwise, you know, otherwise I wouldn't need this thing, you know? Let's say I take it away, please don't think we don't need it, but for a moment I take this away, right? This would be like classical teleportation, right? Because I can put the source inside this machine and I have a preparation machine, right? So this cannot be the case. So some signal, you are totally right with your intuition. Thank you very much for for being so vague. And you should really think more about these things, because you have a very good intuition. Something must travel back to the source or and up here. But I mean, these things, they were sent out at a certain time point. So the first thing that happens is we share our particles. You know, I send one to you and I send one to him. You know? And then him or her. And then she makes, let's call this person Alice. You know, and this person Bob. Then Alice makes a measurement on the two particles, on her two particles. Maybe one that comes from outside and one that she got from the source. And then Bob makes a measurement. And indeed, in this measurement, something changes. And this depends also on this thing. Okay. And I just want to say this was a very great observation that, of course, it cannot. We just can forget about this. This is very important, and it can only serve to kind of wire the correlations, transfer something to the other side. Okay, but what this is another kind of magic thing. It's entanglement. You know, these are entangled systems, and they are not. Their correlation supersedes all classical. So this is a very special thing, and only because we have this super correlations, we can do this. You can't do that. I mean, classical systems classical information wouldn't make sense. Of course, you can do everything with classical. But let me show you one more thing where you see that we can really do more with the quantum than with the classical. Okay. So the next thing I want to talk about is super dense coding. So super dense coding, one can always ask, how much information can I put into a quantum system? And if I send it to another side, okay, and this guy measures it, then he gets out the classical signal, right? But how many bits can I send, right? And the question is, what is the average information that I can send? You know, a bit is a measure for information. You know, you remember we had this average information that we calculated in the first time. The unit of that I is bit. No, a bit is basically a message that the information that is contained in the message that has an alphabet with two letters only. So either I send the letter A or I send the letter B, and both with equal probability. Then the information when I receive A or B is 1 bit. That is what bit is, right? In information. So here the question is, how much classical information can I put into my quantum system? Here, let's say this 1 qubit, okay? How much classical information can I send? Classical information can I send in here? Can I send through this? What do you think? So, how much classical information can I send in this? What do you think? I mean, in 1 qubit. You must remember 1 qubit, I can only distinguish orthogonal states, and there's only 2 orthogonal states, right? So I can encode, let's say, my light, you know, at the vertical polarization or the horizontal polarization. So I can either say vertical or I can say horizontal. In that case, you know, vertical is maybe 0 and horizontal is 1. So if I send that with probability 0.5, then I have 1 bit. You know, that's it. if I send a vertical and diagonal or so, then no one can distinguish the two. That doesn't help me really. And so I can only send one bit. Okay, can we agree on that? Is everybody happy with that? So I can usually only send one bit. Okay, but now there is a trick how I can put more in. Namely, again, I use the source, by the way, everything that is like an apparatus and not a source is square, and everything else is so source is round. Now I must shortly look on my thing so that I don't do something wrong. So here's again Alice, and there's Bob. And now we have the source, and we send the source particle to Alice, and Alice just does a transformation. And in this case, it's a unitary transformation. I will tell you later what it means. It's just a rotation, a generalized rotation on the vector. Okay, so she does a rotation on the thing. And sends it to Bob, okay? And then Bob makes a measurement on these two particles, and we already know for 2 qubits if this is also qubit, okay? So these are all qubits. Okay? And here is a transformation with A, again, 0, 1, 2, 3. I don't care in which language you write this. Okay, but this is not transferred. So this is just 4 possibilities. And Bob makes a measurement, and he gets also numbers, and these numbers that we call them B, they are also either 0, 1, 2, or 3. And in fact, what he gets out here is 2-bit. Okay, so in this scheme where I support the sending by an entangled pair of qubits, I can actually transport with this qubit 2-bit. Okay. So depending on what she does here, I get here 1 of 4 numbers. She sends by just sending this qubit, but assisted by an entangled pair. She gets across 4 numbers, 1 of 4 numbers with probability, which is 2-bit. Okay, so that's super dense code. All right. So are there questions? Or maybe I write it down so that we. So this is getting worse and worse. Not worse. So it's not good. Alice can send 1 of 4 numbers. In with 1 qubit. This is called superdense code. I'm so sorry that you can't see this. Okay, then I come to the last machine. Alice can send 1 of 4 numbers. Okay, so A equal to 1, 0, 1, 2, 3, using 1 bit, 1 qubit. Okay, so that is she sends 2-bit. 2 bits. How do you say it? Do you say 2-bit or 2 bits? All right, good. So last and not least. Okay, no, nothing. So the last machine, who can guess what the last machine is? You all know it already. We've talked about it a lot in this conference because this is a conference about. Yeah, it's quantum computing. So the last one is of course quantum computing. And of course there are others, there's quantum sensing and so forth, right? But quantum sensing is not really kind of a property of quantum information. It's just a property of the single atoms or the single photons or whatever, because they are so localized, they are fantastic probes with a fantastic resolution, you know, or they are in terms of the atomic clock, you know, the atomic clock is also a quantum technology instrument. But this is based on the quantization of the atom. You know, it has more or less sharp levels, a level structure, and the levels can be used as a frequency standard. And over the frequency standard, you get a time standard, right? So that's not really a thing of quantum information processing. This is just a property of the quantization itself, the discrete level structure. Okay, so I want to talk about. Sorry, I have to first unpack that. Can you unpack that? I first want to talk about quantum computing. So this is for quantum computing. Computers, and it works like this. We have here, for example, a double slit, okay, and then behind the thing here, we get a wave pattern which looks like this, so an interference pattern. So this is the intensity here. The intensity. So most, if I send single photons, okay, and I can even send single electrons too, right? Then what happens is that the first one might arrive here. Then the next one arrives here. Then one here, and so forth. And I see all these hits. This is like a screen, like a photographic plate. Okay. So I see after a few hits. And each photon or each electron I send individually. So all half an hour one. So they cannot see each other, right? And then after some time, I see that here are many, and here are many, there are many, and so forth. And I get this pattern. So where the thing is most black, where most hits happened, that's how I write this curve. You know, that's relative frequency. Okay, so here it's the intensity. Right, so well, I could say the probability, maybe intensity is the wrong word, because you know it assumes that a lot of stuff comes in parallel. Probability. So this pattern here is if the wave that comes, if the state that comes from here is psi A, and this is psi B, then this thing here is psi A plus psi B, right? And if psi A encodes a certain task, you know, so the slit here is made in such a way that it changes the information that is put in such a way that it makes a multiplication of the number x that was in the initial state, and now it multiplies with it multiplies with a, the number x with a, and that is then corresponding to, so say psi goes to psi a, you know, this is kind of corresponding to each other. And the second thing is, the second slit here is slightly differently formed, and it means a multiplication with the number b. Okay. Then somehow in this interference pattern, I have the information about both multiplications. And I can do then so, therefore in parallel. So I send one thing through, and the wave function that comes out encodes both properties. If I now have a way to read it out, I have solved two multiplication problems in one step. But I can also make here more slits. I can make there a fantastic number of slits, let's say 1 million. Okay, then I have 1 million steps in one. I mean, 1 million operations in one step, right? So that's the quantum parallelism that leads to quantum computing. And what is important to know is that even though, listen, so even though we are now in the regime of noisy intermediate size quantum systems. So it's all very noisy. There is in principle a recipe how we can do error correction such that we only get a polynomial overhead. So we can, if we can solve a problem using this thing in polynomial time, then after error correction, we will still be in polynomial time, okay? And there are problems that usually take exponential time, and now with quantum computing, problems to take polynomial time. So we can solve things. For example, the factorization of big numbers can be done in polynomial time using this. And once we have a big enough quantum computer so that we can do the error correction, we will be able to do this in polynomial time. And that is exactly what cracks the RSA algorithm encoding. And other encoding will follow, right? So this is the thing. So even though it's very difficult, as we heard yesterday from Daniel and the day before, to do quantum computing now, and there are already kind of things that are worthwhile to do. I mean, we heard that from, I think from Leonardo in the morning. And the other message, my message is, there is something called quantum error correction that can be shown that it has only a polynomial overhead. Therefore, and only therefore, it is worthwhile to follow this development, because in the end, it will lead to something if we are managing the technical part that is really has a lot more computation power than we have so far. Okay, any questions so far? Maybe let me just also write this down. So can solve, can carry out two computation tasks at the same time, and so simultaneously. And in fact, multiple, or not only two, but many. Okay, so that's that. Right. Are there questions? Yes.
Okay. That's Alice comes in 1 minute. And I was wondering what's advantage is serving as this machine gives.
compared to the classical system in our we've been one of the selling points of humans such as cosmic so in this case, I'm not listening to this so that's advantage of this system. Okay. So of course I can, this is for each photon, but I can of course send many photons. Then I just need many entangled pairs. And then I can use. It's a little bit of thing that I need to be able to address each of the information carriers individually. So I must be able to distinguish it. If I give you here the light from the lamp, wow, thank you so much. The light from the lamp, then there's many photons in there, but how do you distinguish them? So there's Avogadro, 10 up to the 23 photons. If we could use each photon, let's say we would be able to, that would be 10 up to the 23. Fantastic. But how do we do that? We have to mark them. Okay? And one way of marking we will learn more about is in different spatial modes. Polarization you can only have two. But if you look at spatial modes, so the wavefront can have different shapes, and you can have infinitely many different wavefronts. Although that is also not true, because if you take very many, then you need very small wavelengths. That means unfaded electricity. So there is no free lunch, okay? But let's see how far. Okay, so we can distinguish many. We can send many. That's what I think. Right. Thank you for the question. Okay. Yeah.
To the example.
Cryptography. Yes, sure.
So suppose you have a situation. Okay. You and I were working on something. I have quantum information I want you to process for me. And I have a way of reading information. So I don't have to keep them just process it. So I send you the quantum information of the public channel. You do the computation, you send me back quantum response. Right? Possible. Can drop the purchase.
Yeah, of course. Yeah. So there is a famous attack called intercept and resend it. So I get your photo. You don't see me necessarily doing this. I'm somewhere hidden on the long way between Durban and Kumasi. And then I resend the information, right? However, since I don't really know what information is contained in a single token, because I can't measure it, I might make mistakes. Of course, I make a measurement and I do it as good as I can, but I can't do it perfect. That gives me the chance, if you send it to me, the information to me, to actually find out whether someone was listening. So part of the data we have to segregate. In order to recognize the eavesdropper, from time to time we have to just make measurements. See, is there someone in or not? And we can see it. So this is the quantum key distribution has always measurements that are made. Actually, since you are since you try to distill a key, so classical numbers, you have to make measurements anyway with quantum key distribution. I come to your example a little bit later. For quantum key distribution, you anyway do measurements, and then you can also compare some of the data over public channels. That data must be discarded, but it will show both Alice and Bob whether there was eavesdropping. So eavesdropping can be detected. It's the first message. The second message is this also very nice game. So here the idea is, you send me quantum information, and I do the processing. So I'm Bob, I have a quantum computer, which you don't have. So you send me the thing, I do the quantum computation, and I send you back the quantum signal, and you read it out. That is a wonderful thing because it leads to an idea called blind quantum computing, which is that you send me something, I do the task with my computer, but I don't even know the task I'm doing. You know, I mean, you think I must know because my machine must be programmed somehow, but the information about the code might also be in your system. You know, I mean, this was the big idea of Turing. His first name was
Alan Turing.
Alan Turing. Thank you. Of Alan Turing, that he said actually there's no difference between the you know, the algorithm and the data. So it is, both can be written down as data, you know. And so if I send you the information about the algorithm together with the data, with the input data as a quantum system, and you cannot read it, then it's perfect because you use my machine and I can never tell what you get, right? And I can send it back and you read it. That's blind quantum computing. Very important. Very important issue and or application. And of course, in that case, it is possible that someone could come in and change the thing around, and I don't notice it. So again, I would have to make tests, you know, but such tests exist. We can check whether it is. So in principle, we can find it. Thank you. Nice question. Yeah. Yeah, that's again, I mean, I don't know. I will never leave you because you ask best questions I've ever heard. Now I had 3 in a row. So the thing is, the question here was, can we not prevent the eavesdropper from eavesdropping? Well, the point is that we can prevent him from doing it in that sense that we detect that he's there, and then we don't use that information that was sent and that he detected anymore. So he cannot use his information. In that sense, we can prevent him from using the information. From listening itself, I don't think so. I have never thought, but maybe someone has a good idea how you can actually prevent him from doing it. Maybe, you know, ideally his little device explodes or something if he tries it. I don't know. By the way, we have in Durban, we have these key distribution machines, you know, from IDQ, which is a Swiss company. They are the market leader, and we try to resell it, right? That's good for us because we learn a little bit what the clients want, and we make some money that we can put in our research, right? So, and I think everybody should do something like this. Get into this, get your hands dirty, and learn about it. But the thing is, if you open these machines, so we had some water damage, right? And then I said, can I not just open the machine? I mean, it's not working anymore, and see what's inside and repair. And they said, no, that's not possible. If you do that, it will self-destruct. That's really amazing. So these machines, they have to be secure, right? They have military security. So no matter what you do, you cannot get to the information, even not to the information that's stored, you know? So in the moment you try to open the thing, it's like in the James Bond movie, right? So I don't know, please invent something that, you know, if someone is trying to eavesdrop, we will detect him before he actually starts. So that's a cool idea. Thank you very much. Are there more questions? Yeah. Thank you.
You said that to detect eavesdropping, we need to measure the information.
Say it again.
You
Sorry.
said to detect eavesdropping, you need to measure like the information that is being passed across. So and that means that some of it gets destroyed. Does it mean that we have to send along with the information we're sending, we have to send information that we don't need as well.
I absolutely must really record what they say. It's amazing. So, yes, so here's the question. If we have to destroy some of the information, don't we have to send more information than the information that we need? Yes, we have to send more information. And then the question is, can we not send them on a different channel? So that, can we protect information by using some quantum channel with maybe with the classical channel? I'm now extrapolating from your question. Can we protect a classical information channel that is easier to manage and has usually more bandwidth? Can we not protect it using a quantum channel? Can I not send one of the photons with my classical stream of photons and then find out whether there was someone in something like this? Great question. All great research questions. No one has done it. Okay, so yeah, all great ideas. I cannot answer the question. Probably yes. Okay, then I go now. What time is it? That's important. It is now 9:27, so we have done more or less an hour, right? Then I would say take 10 minutes break, and then we go to the measurement thing.
All right.
All right, thank you. Good. Thank you very much for the nice.
It is sleep.
That's
You know, from this time until we struggle sitting straight. We will sleep a lot. I'm telling you, that's why I don't want to get to that.
So now
No, the chance. How? So. No. No, sir. It goes always. And the media, people come. So few now, very few. That's a good idea. I just worried about the screen here. I mean, but, you know, I don't know anyway, watches this. No, I mean, that's the. Hey, that's important, that actually mirrors your images.
Okay, if you're ready, we can start. On 9:40. Yeah, so now I want to talk about quantum measurement. Okay, quantum measurement. So let's try to do it at examples, right? So first I give you the usual textbook description of a measurement, which is very abstract. You know, I mean this whole field is very abstract because information theory itself was already very abstract, right? But we have to always remind ourselves what is the physical reality, because otherwise we think it is, or we are not able to engineer this. You know, I mean, you have to be able to come back to the level where things actually happen, you know, and they are not just information. So first, I think this was number 2. The first thing is example. And there is a famous experiment from 1922 called the Stern-Gerlach experiment. And it's about measuring spin of spin-a-half system. All right. So Stern and Gerlach, they were two Stern was, I think Stern was an experimental physicist and Gerlach was a theoretician. And they made this experiment in 1922 in December. So during Christmas, actually after Christmas, shortly after Christmas, they went away from their families to the lab. And they sat in the lab and tried to do this thing. And they were totally surprised by what they saw. And that's why this experiment became famous. They thought that after so they watched atoms flying either up or down, all right? And they thought that this shows that somehow space itself is quantized, that there is some kind of either you go up or you go down. So the direction which you fly is quantized. You know, that was very strange for them. And they wrote a paper about it, and later only people found out this about spin. They didn't know that spin exists. You know? It was a new quantity. And once you know what it is, it looks simple. It's called the spin-a-half system. And it can be written, it's like a cube, it is a qubit with a 2-dimensional Hilbert space. I make this 2 here. And it's given by 2 basis states, or the span of 2 basis states. Maybe the basis state up, we can now invent a new way of writing things, and spin up. I can also identify that with my 0 that I set, and spin down. Right? So basically, these are 2 orthogonal vectors. Okay, and these are also orthogonal vectors. I mean, I just write this differently. This is just a different notation for this thing. And anyway, what is this? No, I mean, it's just a symbol for something, right? But it symbolizes a system that is spin up. You know, it's spin up and say spin up and spin down. And like I say, I want to keep it very abstract because then I get an easy description, and later I go into the physics, and then we see what it actually is. So there is an observable.
And this observable is called SZ for this Z direction of the spin. So there's some Z direction here. No, X, Y. And now I want to know the spin in Z direction. And I can write it, I can represent it using one of the Pauli matrices and some value here called H bar, where H is the is Planck's constant, and sigma Z can be written as 0, 0, minus 1, 1. So these things are projectors that are made out of this cat here, right? And a projector is a nice thing because it projects onto the state, right? So if I take any state, let me just write this like this. If I take any state and I use this projector onto it, then this just means that I take the state and put this thing here, this cat, you know, the symbol cat represents the state of the system. And I use the symbol psi here, and I just put it behind this symbol. The symbol is called a graph. And this is a graph. And in the projection, I can just, you know, you see here's an extra vertical line, and that comes together with this line, and that in the formulas becomes one line. And then I have this thing, a bra and a cat together. And now I want you to read for me behind each other, bra and cat. Say bra and cat, but fast behind each other.
Bracket.
Bracket, right?
Bracket.
Bracket means bracket. That's where it comes from. Okay. Bracket. Okay. So it's a bracket. And the bracket is the inner product. It's just you know, you map a vector onto a number, or better, you map you can also say you map two vectors onto a number. Okay, the vector psi and the vector 0, or you can read it as this thing here is a linear function that acts onto this vector, so it maps a vector onto a number, right? And the bras, they stand for function vector. Do we call it function? Linear function, is that a word that we use? Okay, so it's a mapping from the vector space into the field, into the numbers, okay? And this is the inner product, okay? And so that gives a number, right? And we can calculate that number. Let me do it for you. And let's try to do this. Let's say psi is some coefficient C0 times 0 plus C1 times 1. Okay. Then if I put this in here, 0, 0, E0, 0 plus C1, 1. Right? Then this is equal to I can now put the C0 outside. Now in this inner product, the C0 can be put in front of this thing, and it can actually be put in front of this thing. So I get C0 and then 0, 0, 0, okay, plus C1, 0, 0, 1. Do you see what I did? I just, in this inner product, I replaced the psi by the expression. It's a general linear combination of 0 and 1. Physics would say superposition of 0 and 1. To say 0 and 1. And then I use the linearity of the inner product in the second component. Inner product is a linear map, you know, in the second component. So this thing is a linear function.
So I can pull the C0 in front. And in fact, in this formalism, you can pull everything in front of everything else, right? That's very curious. And then you get this thing, yeah? And now we just have to know what 0, 0 is. The inner product of 0 with itself. That is the norm squared of 0, of the vector 0. And all vectors we are dealing with are always normalized, okay? So this is always equal to 1. And this thing here, since they are orthogonal, this is always equal to 0. So what I find out here is that the whole thing is nothing else than C0, 0. Okay. So what happened is I projected this state onto its 0 component. And so the vector that comes out is a vector that doesn't have unit length. It has a length that is connected to the C0 coefficient, right? And if I really want to calculate further in the formalism of quantum mechanics, I have to normalize this later, right? But this was just a mathematical operation, not a physical thing. So I don't worry about it. I just wanted to show you how these calculations are. And this is all you need to know. You don't need to know more in this whole business than how to calculate inner products. And you need to know that there is a basis and that it's always an orthonormal basis. And then you can always express everything easily in one sentence. Okay. So the nice thing about quantum technology or quantum computing or even these measurements getting on the abstract levels, it's super simple. I can teach that, and I've taught it to learners from high schools. They understand this because, you know, it's not difficult to do these things. Once you overcome your fear of the abstract, okay? But we get more concrete now. So this was just a small interview. Okay, this was just a side fact. Now I want to describe this in terms of measurements, okay? And I actually, if you allow me, I will call, because I did it here in my script, and I can know myself, I will confuse myself. Do you allow me if I call the psi phi? You might.
Yes, sir.
Okay, thank you. So that is a phi now, instead of the psi, because I need the psi for something else. But that's fine. And now I want to actually tell you what physically happens. So physically, I don't know, can you see this? Oh. Okay, let me try it. Okay, so physically, I have now a preparation machine, right? And it prepares maybe the state phi. Goes into measurement machine. So I say this is the state psi, phi, which is basically the quantum information. And now the thing makes a measurement, right? And it gets one of two outcomes. So in this case, it gets an outcome, let's say, let me call this B equal to H bar half. So, funnily enough, always what is in front of these projectors, this thing here is called an eigenvalue of this observable, and the measurement results are always the eigenvalues. This is just a formalism, how they invented it. You know, we call them also spectral values, okay, the eigenvalues, right? And the spectrum comes from these optical experiments where they put light onto atoms and then they saw certain absorption lines or certain emission lines, and they had the wavelengths, okay? And that was the spectrum. And it turned out that the wavelength was related to the image, that image. And then they could somehow map this, and they wrote down spectral decomposition means actually really the physical spectrum before it meant anything else in mathematics. The mathematicians got these problems from the physicists. Okay, so the eigenvalue is the measurement result, and here we could have the negative measurement result. Okay, and I want to distinguish these two cases, and I want to make it such that actually the measurement apparatus is not only giving me that, it also has to give me the system back, because where's the system? I mean, so far, I only said, yeah, some system goes in, then there's a measurement and some classical information comes out. That's a nice description. But what happened actually to the system, to the quantum system? Maybe it's still there, right? So you can imagine a measurement apparatus where, together with the classical signal, you also get the system back. And then the system will be in some state, psi h bar half, you know, let's say, maybe I call it psi plus, like phi plus. Okay, and here it will come in state phi minus, because the difference between the two is this has plus h bar, this minus. Okay, so I call them phi plus and phi minus. And of course, I want to know two things. First, what is the probability for the measurement result? And second, what is the state after the measurement? So I know these two things, I know what the measurement is. In the in-out formalism. Okay. Later, in a moment, I describe it in the physical, in time. You know, what happens in time? How is the dynamics of this process? That's a good question. But on the abstract level, it's in-out. It's a black box. Okay. So how do we calculate the probability for plus h bar half? Well, that probability is calculated by taking the expectation value, the expectation value of the projector onto the state that belongs to the eigenvalue. So the eigenvalue plus h bar half is connected or associated with the state 0, while the eigenstate minus while the eigenvalue minus h bar half is associated with the eigenvector 1. Okay, so let me maybe also write that down because I finish. So what we have to do is we have to take the projector onto the eigenvector that belongs to the eigenvalue and calculate the expectation value of that. Then we get the probability. Sounds very complicated, right? It's known as Born's rule. Okay, and I write it in this complicated way because I want to generalize it in a moment. Okay, it's Born's rule. So let's calculate this thing for me, please. Okay, so I want to calculate this. How can I do that? So I write. You see, now I can the magic of this formalism is called the Dirac formalism. This whole thing, the Dirac formalism. So Katz and Brass, this is the Dirac formalism after Paul Dirac, who invented it. Dirac formalism. And if the magic of the Dirac formalism is that I can make the brackets wherever I want. Okay, so I write this thing here now in such a way that I make the brackets like this. So what you see is I split this thing here in two objects. This is the bra, this is the cat. And then I put the brackets around these two
which led to this inner product. And I put the brackets around these two, which leads to this inner product, right? So that was a nice trick. And now I can actually look at this and I see, aha, this thing here must be the complex conjugated of this, because this is the inner product and the field is the complex number. And inner product on a complex space is antisymmetric. That means if I change the arguments, I get a complex conjugate. This was a lot of words. And for those of you that don't know about this, don't worry about it. It's just one of these technicalities. But we can write this thing here basically as 0, 5, and then complex conjugate. This is my sign for complex conjugate times 0, 5. Okay, and this is nothing else than 0, 5 modulus squared. So this thing here is Born's rule. This is how Born wrote it. This is how we write it down nowadays, right? But this is what Born actually wrote down. And before he wrote that down, it's actually very interesting to read his paper from 1927 or so could be, where he formulates this for the first time. He first left this out, the square. He said, no, the probability is just a modulus. And then there's a footnote where he says, I thank the referee for pointing out the Euclidean square. Okay. And then 30 years later, he got a Nobel Prize. You know the referee. But those were the days where even ordinary people could make extraordinary discoveries. That is when something is at the beginning. Then even people like me can make a discovery because it's not enough. You know, because in the beginning it's easy. If you come in 20 years' time and you want to do quantum technology, we have to sit together for not a week, but for 10 years until we understand everything that happened in the last 20 years. And then it's too late, you know. But now is the time where you can do it now. You know, I teach you here a few rules and you come up with your own ideas. You know? So that is, so this is the time to get involved with this. I mean, there were two phases. The first phase, quantum technology, was the first quantum revolution. They applied this to all kinds of physical systems. They discovered the transistor. Okay, the transistor made all this progress possible in electronics. You wouldn't have cell phones without the transistor. Okay, and that was the laser. First one. Second quantum revolution is now, because now you can actually isolate single photons. Can look at single photons, single atoms, and that gives us a total new plate. Okay. The founding fathers, Schrödinger said you will never to see what's single atoms. Right. So this is this. And now I want you to calculate what this is. Okay, so here we have phi, this thing, and I want you to calculate with your neighbor what is the probability to get h bar half if the system that comes in is in state phi. Okay, so 3 minutes each of you, or together, together with your neighbor, and I come and ask it after you.
Too far. We're engineers. What? Let's have the probability of h bar half, given that psi is equal to C0 plus 0 plus C1.
That's
Yeah, it's 6. So what is the probability? Like, so,
you just each one have
Oh, yes.
one and both.
it's
This reminds me every time after every report and just make a folder for it because you know these notes are better than my notes. And my notes, not saying my notes are partly in German. Then I cannot copy them. You know, Professor Martin will always sends me emails in the night. Put up the lecture notes now. No, he's not that. But you know, otherwise I sit there and I.
So I keep going. Go to a play fair, so it's there that the kind of. Yeah, this. Okay, so this is. Right, five. Now, first, right, see. This is a great practice. And you know, yeah, so just to repeat, this is the inner product, right? So some people would write it maybe with vector signs on top of it, you know, with a comma entry. But in the Dirac formalism, we just leave to write a vector sign because everything here is a vector. And we make this instead of comma, we make this thing so that we get the bracket, okay? So you just have to now take this here, write it as as this here, it's here plus 1. And then you have to calculate this thing by using the linearity, and then leave away the one thing in that product of 0, 0, that product of 0, 1, and use the one moment. And you have to square. You're going to be scary.
Yes. And the linearity or the linear sequence. Yes. So that's
Okay, so let me ask someone somewhere. Yes, this. You just have Okay, so what's the answer? So the answer is CP naught squared. Why? Because you can use the linearity by writing C0 is plus C1 and then 0, 1. Okay, and this here is so sorry. This here is. Are you still with me? Hello. I need you. Okay, thank you. So that gives me 0 because they are orthogonal, and this gives me 1. So I get C0, and now I have to calculate the square. So I calculate the square. I calculate the square. I calculate the square. So the answer is the probability. The probability is equal to modulus of C0 squared. Probability of H bar is equal to modulus of C0 squared. Okay, and that's easy. So if you see a vector like this, and someone asks, what's the probability to project onto 0? And you say, it's this component modulus squared. Okay. If someone asks, what's the probability to measure minus h bar half, that would be projecting onto that thing, then I say it's C1 squared, modulus squared. Okay, so that's the whole thing. Not more difficult than that. And now I want to write down the state after the measurement. Okay, but before I do that, I take a photograph. You are reminding me. Thank you. Because this is our lecture notes at the moment. Okay, we can.
You also take a picture.
Not so sure. So we have to. I have to do this. Can you still see? Okay, great. So now next page. So what's the measurement doing? What's the state after the measurement? We now calculate the probability for these outcomes, for this classical outcome. But what is the state after the measurement? Well, we said it already. It's a projection onto the states, onto the eigenstates. Let me maybe write down again eigenstates. So the eigenvalue equation for a stat is if I put a 0 there, okay, then you get h bar half 0. And if I put a 1 there, you get minus h bar half 1. And please check that for me. You know, this is also exercise. You just put in a stat is equal to h bar half 0, 0, minus 1, 1. All right. And if you put a 0 here, the 0 onto the 1 gives nothing, the 0. So this falls away. The 0 onto the 0 gives a 0. So I get h bar half 0 here. And if I put a 1 there, then this gives a 1 and this gives 0. So I end up with minus h bar half 1. This is the whole trick. Okay. So say this is clear. So that this is the eigenvalue equation for this set. And now state after the measurement. Okay. What's the state after that? So the state. Right. Okay, state after the measurement works like this. I have psi. I have psi and phi, and the phi goes to for plus h bar half. It goes to the corresponding projector onto the eigenvector. So h bar half plus h bar half is the eigenvector of 0. And I need to get the projector that corresponds to the h bar half and write it in front of the phi. Okay. And I need to divide by the square root of the probability. That sounds complicated. So I write it in terms of 0. Sorry, phi. I write the phi, and then I have 0, 0, phi. This is the probability, maybe you recognize it. And this is the thing. So I'm calculating this. This is 0. Okay, and from here I get the C1. Okay, and then divided. This one is C1 squared, just calculated it. But since I have the square root of it, I just keep the right way the square. And then if I write C1, I can always write as modulus times space. Sorry, this was zero. Okay, so I can any complex number I can write in terms of modulus times here up to the I phi 0, right? This is just one of the tricks that one can use. And then if I divide it by each other, so I get e up to the I phi 0 times 0. This is the result. And now the trick is that actually I can just write 0. It corresponds to 0 because this is a phase in front of the state vector, and that you can never measure. Why not? Because in all measurements, you have this inner products, And you see, if I have probabilities, here I have a phi, and here I have phi. And this thing here, if I write the corresponding graph to this cat, then I get a factor e up to the minus I phi 0. If I call this thing here, I call this thing here, let me call this phi plus. Okay, if I write phi plus, this would be e up to the minus I phi 0, 0. So this factor in the inner product together with the e up to the I phi factor from here, we would always get 1. You know, this would cancel against this one. You see, so you never see a global phase. Phases you can just forget. At least these global phases means a phase in front of the whole cat. They cannot be measured because everything is measured in terms of these inner products. All right, so we have that. This is the state after the measurement. So that's fine. But now we have to do the real thing, okay? So this was the abstract way of describing it. We know what the probability is. The probability is C0 squared. It's the expectation value of the projector to the corresponding eigenstate. So you see these things, they play a role, these projectors. That's very important. So if you have the spectral decomposition, you see these projectors, and the projectors correspond to the eigenvalues as well. So this projector corresponds to this eigenvalue, and this projector you know minus sigma half. So now I can write it like this. This is the spectral decomposition, right? And if I want to calculate the probability that I measure this thing, then I have to take expectation value. Expectation value is this construction. That gives me the average value that I get when I measure this. So in this case, the probability, that was a better explanation, but so the expectation value of this thing is basically expression. And the expectation value of this would give me the probability measurement. And then for the measurement, for the state after the measurement, I also need the corresponding projector. I have to write it in front of the state and then normalize it as a normalization factor. And then I get out the final state after the measurement. In this case, it's 0. All right. Are there questions concerning this? Was a little bit much. I understand that. But now I'm going to physically motivate it. Okay, so I'm going to write down the physics of it. What happens in the machine? If I have enough time. 10:24, not really, huh? Not really. But it doesn't matter. We have still 2 hours and a half. Don't worry. We have enough time, okay? So I would say that that we take it step by step. So first give me some questions and then we stop here. And then we go on later this afternoon. Is that okay or do you want to continue? It's okay.
So let's go.
You've seen enough. All right, but questions? Yes.
Sit down.
Let's
Yeah, it will come. When I come,
Yeah. These things have been loud.
I do the YouTube, like the Bluetooth to see YouTube massive. They have a way in the connectors. They say,
Can I take it
go to
away?
your, it's not you, it's not you.
You want to do coffee?
Then go to something Jabra. Go come. Yes, a casa one. About. Okay. All right. Let's continue again.
C'est qui est d'accord, ça?
Yeah.
Ça fait longtemps que ça fait bien, là.
Hey, no, nothing on this. Ah, another Francis.
This is a meeting info.
So should I say, I mean, should I,
This is a meeting.
should I use that one?
Yeah.
Yeah, I mean, it's just something I wanted to show them because I want to share with them something on Google, something, but I don't know whether they got that. Let me see. I think it's really projected, right? So Zoom. Which this which one? Did you roll or cancel? connected a couple of days ago. Maybe I should maybe remember. It's a bit slow, I don't know why. But also the hotel is the same. It takes a while, but then it works. It looks good. You can see it already.
915,
915,
85,
5,
84, 87.
4, 8, 915, 829, 584, 84. 9,
75,
75,
71,
71,
62.
62. Thank you. Fantastic. Thank you very much.
No. Wait. It's good. I can take it away. Well, yes. No. No.
Are you all ready to go? So, okay, so I was told the mic as well as Thomas. And then for those sitting very much in the back, it's fine if you do something else. So let's say if you were interested in what I'm going to tell, it might be better you move as much forward as possible, just because I will also jot down stuff on the board and maybe it's not so easy to see, right? All is well. Well, I will also move it then, but at the moment I will just go through what is now projected. And whenever there's something you don't see or something like this, shout. Okay, good. So I said now Henry put me in your WhatsApp of the school. So yesterday evening I still sent you a message telling that I had put some material, some lecture notes of a longer serial of lectures which I gave elsewhere some time ago on this Google site. I also put this quiz with the list of questions on which you want to go now at the beginning to go a little bit to recap a bit what we did last time. But then I got a message from one of you, I forgot the name at the moment, who sent me a WhatsApp asking which site. So who did find this material? Or who knows which site I'm talking about? Because I actually don't know precisely which site I'm talking about. So just put it where I was told to do it. So who found this stuff? Okay, who did not find this stuff? Or who did not look for it and who did not look for it? There's anyone, yeah. So those who know where to find it, where the others where to find it. Make sure. Yes. Okay. Great. Okay. Thank you very much. So it's more. Sorry. Sorry. Okay, so the idea was now to go a little bit through these questions, just to see what was the cross section last time, right? So first question, name two physical realizations of two-level system. So any suggestions? Two physical realizations of two-level system. Any suggestion? Yes, this one. Give your name, please. Women, okay. They try to tell what me and the last I mean, does two natural atoms, which the experimentalists find in nature, do they have just two levels? The hydrogen atom. Now, does the hydrogen atom does it have only two levels? How many levels does it have? Anybody knows how many levels the hydrogen atom has? I mean, 2, 3, 4, 5, many, even more. Okay. Who said one? Yes, okay. Please give me your name. So if of course, I will not remember all of it, but I will try. This is set, right? So one level of the hydrogen. But then if the hydrogen atom had only one level, how could the hydrogen atom absorb a photon? So you see, it's not plausible, right? So there must be at least two levels, right? So, and maybe somebody else has a suggestion how many levels the hydrogen atom has? You have a suggestion? Can you learn this? I wanted to ask. Suggest. Yeah, which is? Perfect. Great. So we'll see what happens, right? So this you learned from reading Thomas's lecture right now, right? Okay, here's another one. I'm trying to learn the name right for the both of you. So okay. So now we come back to the hydrogen atom. I wrote that down there. So how many levels does a hydrogen? I mean, what's the potential of the hydrogen which creates the binding, which is the binding potential for the electron in the hydrogen atom? So is this harmonic oscillator? Is this like quadratic? Or we have like, I mean, what's the force which keeps the electron, which binds the electron to the nucleus? It's so Coulomb force, right? So then what's the potential what's the Coulomb force? It's function of spatial coordinate. Okay, these are these constants which theoreticians you see they always put them equal to 1, right? And we just say, but let's say okay, so there's these 13 electron volts, fine, yeah, but let's say what's then the dependence on the distance of the electrons of the nucleus? Like two charges interact. Do you have questions there? Do you want to explain something? No. Yes, suggestion. What's the Coulombic force between two charges? How does it depend on the distance? One over r squared, exactly, one over distance squared, right? So then what is the potential? If the force is 1 over r squared, then what is the potential? 1 over r, right? Right. Okay, 1 over r, right? So it's a 1 over r potential, right? And so therefore the potential gets weaker and weaker as it goes higher. So then how do you imagine if the potential you have such a potential, right? That's you. So that's the distance. G over r. So then how will you imagine do the energy levels lie? So you have the ground state, right? So you have the ground state at -1/2 in suitable units, right? That's the energy axis. Also the energy axis, right? And then so here's 0, right? So when the electron has positive energy, then what happens to the electron? Positive energy, what happens to the electron? Does it still winner? Yeah. When it's at positive energy, what? And speak out of it, winner, please. Yes, but assume it's in an excited state with positive energy. Then it says, it can be fixed state, cannot or can. Can't. Okay. Yes, assume it can. I mean, let's say we still have to discuss, but what's important is that I mean the state of positive energy are called the continuum, right? Then the electron is not bound anymore, so then it's ionized, right? So this happens when you absorb the latest some there's a field which is called ATO science. Where you can otherwise for Henriet in a few years ago, I think 2023, I guess, right? Nobel Prize. And there you send in photons such that you come up here, right? And then you ionize the electron, and then you measure the photo-ionized electron, right? That's correct. But then typically this electron goes away and it doesn't and it's just detected and the game is over, right? Now, but let's say if you have a second level here, right? So then can, for example, so a photon of a certain frequency omega, right? And then after some time the electron will emit this photon again, right? And that's why we can see this light which we saw when for example, when I showed you this movie of the quantum register, where we saw the atoms being bright and suddenly get dark, right? Okay, and so I mean, let's say if the potential gets, so to say, if the slope of the potential gets smaller and smaller, how do you imagine would the energy? Do you have an idea how the energy levels, whether the distance of the energy level is equidistant or whether the distance will change? And if so, if it will change, how it will change? Idea? So it's getting wider and wider, so the confinement is getting weaker and weaker, right? So the force is getting weaker, the binding force is getting weaker and weaker. And that's what you also need in quantum dot, what you also use in quantum dots, right? So you call this confinement quantization, right? And if the confinement gets weaker, right? So there's weaker binding force, so the electron is less bound, right? And as a matter of fact, the energy levels get closer and closer. So they get ever denser, right? And so actually the energies of the hydrogen atom, right? They are given by -1/2n², right? So yeah, so now I took away this constant which you named, right? But there's this 1/2n², n is the principal quantum number, and so you see again infinity many, I mean the hydrogen atom has infinity many levels, right? Up to here. Then it has a continuum of levels actually there, right? But it has infinitely many bound states, right? And of which then you isolate two to get your two-level atom, right? Okay, good. So question one is fine. So we have the 2.5, the 3.5 system. We have the two levels isolated within a hydrogen atom. Any other thing from solid state physics? Was one more example I had given, and which you also find actually in the lecture notes at the beginning of the lecture notes, which I put on the web. Yes, double work potential. So what's in this double work? Okay. This thing. Which so then you have, for example, the state left or right, which give you the computational basis states, right? So these then you call 0 and 1, and that's your computational basis state you want to compute, right? Questions on this? No. Question number 2. Which is the Hamiltonian describing the single mode of the quantized electromagnetic, which I also read it by EM field? Which is the Hamiltonian of the quantized electromagnetic field? The Hamiltonian is, so to say, the energy operator. Which is the Hamiltonian? What did we talk about last time? Anybody who has a suggestion, please pick up. This is the Hamiltonian. Which I can say. Okay, no, you're right. Yeah, please. No, yeah, you're right. Yeah, okay. Please. H harmonic equals H bar and Jacobo, you have to speak up, please. They want to hear you. Yeah, bravo. Look. Yeah. Plus 1/2, right? Yeah. I mean, now if I'm very picky, is there something missing here? Will? Identity. No. Okay, right. So I'm picky, right, because this is a number, so it's just a scalar, right? And this is an operator, and since on the right left-hand side must be an operator, so I must put the identity here, right? Okay, Tima. So that's the Hamiltonian describing a single mode of the quantized electromagnetic field. What do I have to? What is implicit here when I have this single mode? Which quantity did I fix when I fixed the single mode? That we discussed at the beginning of last time. So what do I need to fix when I tell the experimentalist which mode has to be prepared? So sunglasses, they will use what? Which property of the polarization? Yes. Then frequency is omega, right? And what else? What's the last thing? Let's say the light ray can go in different directions, right? And what fixes the direction of the light ray? It's a vector, right? And so it fixes the direction of the wave, so it's the wave vector, right? Okay. So what is a photon when associated with a single mode of the quantized electromagnetic field? So now it gets a little bit conceptually a bit more deep. So what is a photon when associated with a single mode of the quantized electromagnetic field? So what formally is a photon? It's an excitation. Yeah. So this is visit. Okay, so it's an excitation, just an excitation, single excitation of this quantum harmonic oscillator. which is the action of the photonic annihilation creation operator upon an energy eigenstate of the quantized single mode electromagnetic field. So what is the eigenstate of the quantized electromagnetic field? So that's these states. These are these states, right? So quantized, that's the quantized energy levels. By the way, they are equidistant, right? That's important. It's the distance is always omega, right? Which you see actually from here, right? And now, so this was n equals 0. This was n equals 1. N equals 2. And so the question is now, what is the action of A upon such an eigenstate? So what's the action of A upon an energy eigenstate with n photons? It absorbs the photon. It destroys the photon. Who absorbs the photon? This is now relatively important. So who absorbs the photon? So A extracts the photon from the harmonic oscillator, right? And later, actually, in the atomic, which we wrote down last time in full glory, right? The atom absorbs the photon. Favor. So and then important, so we get n minus 1, right? So we make this transition to having one less photon in the cavity. And then what's the prefactor? And A dagger upon n. Routine, right? N plus 1 and prefactor. So then which is the formula of the Hamiltonian of a two-level atom coupled to a single quantized mode of the electromagnetic fields in terms of the annihilation creation operators associated with the atomic and with the electromagnetic degree of freedom, respectively. Right? But doing very well. So we need this. We take this way. Volunteers. So which is the Hamiltonian of a two-level atom interacting with a single mode of quantized electromagnetic field in terms of the annihilation and creation operators associated with the atomic and with the electromagnetic degree of freedom. So I had not named them explicitly, or I had not actually spelled them out for the atomic degree of freedom, but I have named them for the photonic degree of freedom, right? So that's the annihilation and creation operator of the photonic, of the electromagnetic degree of freedom. Now for the atomic degree of freedom, we also had introduced operators which transform the ground state into the excited state, and the excited state into the ground state, right? So therefore, in some sense, you create an excitation in the atom, and you destroy an excitation in the atom, right? So therefore, you can call them the atomic creation annihilation operators. And which were these? Start with. Which were the objects? How had we called them? We call them sigma and sigma plus, right? Those are sigma and sigma plus. These were the atomic annihilation and creation operator. Now, is this readable? Yes, yes. Yeah, also the back. Yes. Thank you. Okay, so now in terms of each side, right, and we had the sigma on E is G, right? And sigma dagger on G is E. So now in terms of these guys and of these guys, what is the Hamiltonian which describes the interaction of the quantized electromagnetic field with the two-level atom in full glory. So that's one of the last equations which we had written down last time. So we need the Hamiltonian has this structure, H equals H atom plus H harmonic oscillator for the field, right? Plus interaction. We need a roadblock here. Next time you come out, you warn me, please. Okay, so now what was the form of this H atomic? This was given, this was simple. So this is 1/2 omega sigma z, Pauli z, right? And then plus harmonic oscillator, we have written it already somewhere. So we have H bar omega A dagger A plus 1/2 identity. And then plus, how have we finally then put up the interaction in what you call dipole approximation? So it was dipole approximation, right? Because I considered the atomic dipole, which is formed by the proton and the electron, if I take a hydrogen atom. So I have a separation of charges, which forms a dipole. And I just consider the energy of this dipole in an oscillating electromagnetic external field, right? This has a form x times cosine omega t times the amplitude of the field, right? If provided, I assume driving field is linearly polarized and the k vector is directing in z direction. So then the polarization will be in the transverse plane of the z direction, and I just fix it along x, so I fix my coordinate system accordingly, right? And then I translated this in creation annihilation operators and garnished, so to say, absorbed all the rest in a coupling constant G, coupling strength G. So what was this form then? Somebody can make a suggestion? Was this, no? Who wants to suggest something? Ashra? Yeah.
H bar.
They want to hear.
H bar.
Bravo. H bar G.
A plus A.
A plus A dagger. Yeah.
I mean, sigma plus sigma plus.
Sigma plus Sigma plus Sigma dagger. Prima. Super. Ja. Sehr schön. Nice. Right. Anything in this question? No, just this here degree of freedom, right? And I will call it DOF, right? So also in religion you find that, right? So that's now the Hamiltonian which we are trying to solve later. But you still have a little bit of a different question. Yeah, which are the essential building blocks of an optical cavity or of a resonator? Which are you want to construct a resonator? What do you need with it? Mirrors. That's yes. Okay. So typically these mirrors look like this. What I'm trying to sketch here are the nodal lines of the modes, right, of the standing wave, which are defined by these mirrors, right? And actually, this is this brings me actually to a suggestion. I'm not sure. Did Henry already ask you? I mean, I have in my computer, I have a copy of a documentary, which is actually not on the market, right? Of a documentary on some quantum opticians who work on, how should I say, on creating the basic building blocks for quantum computers in the lab. The documentary, 40 minutes, it's interviews, right? It has been done by an artist, right? So it's not very technical, right? But I think it's a nice documentary movie. Would you be interested to see that? Or let's put it this way, who would be interested to see that? Nice. So it's really a nice movie. The initiative has been taken by Sabina Maniscalco, who is a colleague of mine. She's working in Finland, right? She's originally from Sicily, Italy. And it has actually also interviews with Salvador Roche. Who knows Salvador Roche? Salvador Roche. Who knows the name? One? Nobody else? No? So he got the Nobel Prize in physics, something like, I think 2007 or so, maybe, up to 12 years later. Yeah? So the movie is earlier, so he hadn't got the prize yet. Let's say they were working essentially on isolating single photons, right? We talked last time that they need to isolate single quantum objects, right? Quantum computers, right? I mean, which I showed you in this movie, right? These single ions. And he started to isolate single photons. And actually, there were several generations of PhD students who did nothing else but just working on the mirrors here, right? So just essentially polishing mirrors, right? So because you want, let's say, you see, let's say, if you want to experiment with these single photons, right? On the one hand, you want to be able to, to interact with these photons, for example, to inject atoms so that they can interact with these single photons, right? On the other hand, you want to make sure that the photon, once it's in there, it doesn't go out, right? And so, do you know what's the characteristic quantity which characterizes the time a photon remains in the cavity? So you put the photon in the cavity, and then you see it will go and it will be reflected, go forward and backwards between these mirrors, right? But at some point it gets off axis, right? And then it may leave the cavity, right? Just by specular reflection. And so essentially the inverse lifetime of essentially the number of round trip times the photon takes the cavity before it leaves the cavity. That's what is called the quality factor, right? So that's the quality factor of the cavity, so in terms of the quality of the cavity, so how long you can store photons, right? And for this, I think probably something like 10 PhD theses have been written how you properly polish the cavity to get your stuff. Actually, the movie talks a bit about that. Right? So it's a major achievement to do that, right? And I come back to say. Okay, so we have these mirrors, good. And then now, right, this one, recalling. So who ever enjoyed theoretical electrodynamics lectures? Who can recall, who can remember yes, Thomas, yes, anybody else? Or just electrodynamics, classical electrodynamics, who has seen classical electrodynamics? Yes, don't be shy, I want to see that. I need now some people. Okay, so that's the theory, how you describe. Okay, so who had the opportunity to follow these lectures without enjoying them? That's more, okay. So it's a complicated theory, right? So now, do you remember, do you have some memory of your electrodynamics lecture, which might make it appear plausible that actually you can identify a single mode of the electromagnetic field with a harmonic oscillator? Do you remember still the expression for the energy density of the free electromagnetic field? Energy density of the free electromagnetic field. So that's actually given by the sum of the square of the electric field and the sum and the square of the magnetic field. So it has a form. So it has a form H E M classical, right? Is proportional, something like E squared plus B squared. Or to be exact, still, since I say it's the energy density, you still have to then to integrate over the volume within which you confine the electromagnetic field, like for example, the volume of this cavity, right? This gives you then the classical energy which is stored in this field, right? And you see that this is the quadratic form, right? And then when you do the technical quantization of the electromagnetic field, you do nothing else, but you start essentially from that, right? And then you get expressions from the E field and B field, and since they are quadratic, you end up, that's the reason why you end up with a harmonic oscillator. Okay, good, so let me scroll down. Can I scroll down here? No, I have to go out there just a moment. Okay. Share again. Okay. Yes, and then when driving the atom by an electromagnetic field, under which condition do you expect energy transfer between both groups of fields to be most effective? Which paradigmatic model of classical mechanics provides this the right intuition? So we have essentially this frequency, which is the frequency of the drive, right, which I push, right? And this is the frequency of the that's the eigenvalue frequency of the free atom. So which relation do I expect to be optimal between lowercase omega and uppercase omega to have an optimal energy transfer between 12 degrees of freedom? Sorry. Precisely. So we want that omega is roughly equal to omega. Okay, prima, very good. Nice.
Good. So now we have this. All right, and then the idea of Henry was that maybe
If you were interested, we could watch the movie on Friday evening, and then we would maybe have some drinks or something like this, and some popcorn or something.
okay, good.
Thanks very much. So this was very good already. And maybe just a question for those now who didn't answer and who maybe just looked at the board while I was talking. So is there, do you have a feeling, if this is very far from the subject you're trained in, you have the feeling that there are key issues which you don't understand, some key terminology or something like this, some words which I'm using which are not clear? Can you be willing to bring this up? Biologist is fine, completely fine. No, where did we start not understanding? Right. So the scenario we have, right, is so mirrors, gravity, the restored in cavity. We have the two-level atom. One with computational states and then we have this harmonic oscillator, which represents the cavity, right? This means that they are essentially identical, right? And then we have omega here, this, and we have lowercase omega here. Okay, so now we want to solve the time evolution equation. We want to solve the time evolution equation, which is generated by this Hamiltonian. Okay, so H equals, and I will not write down express now the atomic Hamiltonian and the harmonic oscillator Hamiltonian. That's trivial, right? That's stuff which we know, and we know how these systems evolve individually if we don't couple them, right? And then we have this H bar D, A dagger plus A times sigma dagger plus sigma. And that's V. Right now I say, so this would be something like, I call this H naught, right? So naught, H naught often for the unperturbed Hamiltonian, of which I know everything, I know the evolution. So this is something known, right? Yeah, and so with the time evolution operator U naught of T given by e to the minus I H naught T over H bar, right? And if I already have diagonalized with these, right, and then I have the eigenenergies, right, and then I can immediately know what the time evolution of psi in uncoupled, so if the system is uncoupled, yeah, if these degrees of freedom are uncoupled, so this means V is 0, right? Then psi of t equals e to the minus I h naught t over h bar times psi of t equals 0, right? So what does this mean now? How do I evaluate? Assume I have a well-defined initial state in terms of my computational basis set on the atomic degree of freedom and on the field degree of freedom. So how do I then have to evaluate this expression? What do I use? So when I have given an initial state in a certain basis, right? Then how do I which tool do I use to evaluate this? I mean, because here I have an exponential of an operator. So how do I evaluate the exponential of an operator? How do I mean, be more specific? It's a self-adjoint operator. So then what can I do when I have a self-adjoint operator? How can I evaluate that? What do I need? And I have diagonalized the self-adjoint operator, so I have the eigenvalues, right? Winner, so I have the eigen. Oh, yeah, here we go. No, assume I have the eigenvalues, right? So I assume that actually this part, this I already solved, right? And I want to know how the dynamics of these 2 degrees of freedom changes under this additional coupling, right? So I know what is called the free evolution, which is generated just by h naught, and I say it's generated because the time evolution is given by an exponential in terms of these operators. Therefore, I say h naught is the generator of the dynamics. Okay. So now, but then now I have this abstract. I mean, I have an abstract expression. First I have the operator h0, and then I have a new operator which I define like this, but I write it as the exponential of an operator. Now, how do I evaluate the exponential of an operator? If I have the eigenstates and the eigenenergies of this operator, which is the argument of the exponential. How do I evaluate that? When you're doing this all the time, when you essentially run when you run a quantum function, when you run a quantum algorithm, it's nothing else but a unitary on your quantum register, right? So then what do you do actually when you say, okay, run this, I mean, in this the Hamiltonian then is given in a sequence in terms of a sequence of gates, right? But at the end, it's a Hamiltonian, right, which implements this dynamics, right? And so when you exponentiate this Hamiltonian, how do you evaluate the action of the exponential of a Hamiltonian? What do we need for that? Suggestions? Superposition. Yeah, let's see. Okay. This I can take away. I've seen this picture now. Just important that you keep the picture in mind, right? That you have it. Okay, so I have h naught, right? I have diagonalized, right? So I can write it as sum over j ej times the projectors on these eigenstates, right? So that's a projector, right? And that's the eigenvalues. The eigenvalues are real, right? And these are projectors. So what's the property? What's the characteristic property of a projector? What makes projector a projector? Oh, suggestions? Suggestions? No? But you heard the name again, please. Right? Yeah. The others want to hear you. I know that all you have strong voice, so please use it. Yeah, what's the defining property of a projection operator? So now look, the name is projection. So where originally do you know the name? Which association do you have when you hear projection? From which field of mathematics does this come? From vectors, precisely, or geometry, right? So now assume I mean, this is, let's say, I don't know, that's the x-axis, right? That's the y-axis. Now I have this vector, right? So let's call this, okay, let's call it psi, right? Now, no, let's call it j. No, let's call it psi, right? So now assume, right? So and then what is the projection of psi on x, right? It's this, right? So that's the projection of psi on x, right? So now let's not call this, let's call this not x, but let's call it J1, right? And let's call this J2 as two representatives of the sum up there, right? So then, let's say the projection of psi on x, so this thing here would be in quantum mechanical notation, would be psi on J1, right? Right? This notation is clear. It's a scalar product, right? For mathematicians, that's a scalar product between the vector psi and the vector J1, right? So now what happens if you apply, if you project this again on J1? So you get this object here, which is now this vector here, if I write it as a vector, right? The length is given by J1 of psi. Yeah, and then actually it's times J1, right? Then is the new vector, which I obtain after this projection. Now what happens if I project this image of the projection again on J1 axis? What happens? Nothing happens, right? So precisely that's the characteristic property of the projection operator, right? So if you apply the projection operator several times, it doesn't change anything. Once suffices, right? So projection operator, characteristic property of the projection operator is that J squared J upon J squared equals J upon J. Right? It has a simple geometric explanation, right? So therefore the name is, if you would make sense, if you wish so, right? Okay, good. So that's clear. So now we can take this. Everybody looked at all of that, right? So I can take it away. So, and this property, right? So now, in general, you would also write just now this notation. You would also write Pj is J, right? And then Pj squared equals Pj. Yeah. This is called, they are idempotency. That's the idempotency of projectors, right? So idempotency means that they are self-potent, right? So it's a Latin, it's comes from Latin. Okay, so now you have this Hamiltonian which you expand, and do you know how you call this representation? That's what is called the spectral representation of the operator, right? So that's the spectral or spectral decomposition of H naught. Right? Okay, so now we have the spectral decomposition of H naught, and now, given this, my claim is that I can give an operational prescription on how to evaluate that. So now, if I have the spectral decomposition of H naught, what is the spectral? You have a guess what will be the spectral decomposition of U naught? There's a consultation going on. So what's the result of the consultation? Yeah, it's still on it. Okay. So there's not a spectrum. Is there something you cannot read? Is there something you cannot read? It's fine. Mohammed. So Mohammed, right? So what are you discussing? So what is, do you have a suggestion? That's fine. Not yet. Okay, look. Now let's make a guess, right? So so I would like something like U naught equals, and in principle, if I have a spectral projection, right, it means I would like to have something in terms again of these projection operators, and I would like to have some prefactor here. So which prefactor do you expect does the job? Suggestions? I'm listening. PJ? Oh, no, PJ is already here, right? So that's PJ, right? But I need something here. Here I had EJ, right, for H naught. Now e to the minus I H naught T over H bar. So what would you plug in here? That's it? Yeah, but each, let's say if I put EJ here, right? If I get each sum of the EJ projection J, I would get H naught. I wouldn't get H naught E to the, I wouldn't get this one, E to the minus I H naught T over H bar. But it's different objects, right? So, all right. 1 over H bar. Yeah, not really, no. Anybody? But I mean, who already implemented numerically the action of a unitary on a quantum space? Who did this already? Who did already run a quantum algorithm on an initial integer of the register? Nobody else? But you saw it in the lecture, right? So, okay, so I will tell you, okay, so this is actually, you put e to the minus I, and then you replace H naught by EJ. So that's the spectral representation now of the unitary, which is generated by H naught. And and this is a special, now this is a special, but I mean, probably the most important application, what is called spectral theorem. I mean, Mohammed, is this clear, or can you not, is there something unreadable, or what is it? It's clear, right? It's sum over J, you sum over all eigenstates or eigenvalues. You evaluate the function in which the argument of which is originally the operator, right? With the operator, you replace the operator by its eigenvalue, and you sum over all eigenvalues and take each term, garnish each term by the projector. Okay, on the eigenvector associated with the given eigenvalue. Yeah. And so this is a special application. So this is a special case. Case of what's called a spectral theorem. Yeah, which tells you that if you have a given A, now I make it a little bit more special than the most general case, given A self-adjoint. Yeah, meaning that A equals A dagger, right? For any sufficiently, I mean, I don't write this now, but for any sufficiently non-pathological function f of A, for any f of A, have f of A equals sum over J, f of EJ, J, right? And this is a very, I mean, this is probably one of the key identities which you need to do quantum mechanics, right? I mean, now as I give it to you, who has already seen that? Who has already seen that? Frank, you have seen that? Okay, so. Please take, I mean, if you don't see it from the back, please stand up, right? And to see it, right? It's a very important identity. So if you take this identity with you from this lecture, we make real progress, right? So it says, I repeat it, right? For any self-adjoint operator A, right? Where A self-adjoint is, I mean, it's actually the precise mathematical definition is a bit more complicated, but in essence it says at the adjoint of the operator. So if you represent the operator in a complex value matrix, right? The transpose and complex conjugate of this matrix is the original matrix, right? So then it's self-adjoint, right? For any self-adjoint operator, which we briefly write like A equals to a dagger, right? And for any function, then for any function which is sufficiently non-pathological, so which means essentially you have a Taylor expansion of it, you can Taylor expand it. Yeah? And so for each such function f of A, then for the evaluation of this function, you can evaluate this function by taking the sum over the function originally given, evaluated at the different eigenvalues, times the projector the associated with these eigenvalues. Okay? And you see that this, and you recognize that this has been applied here, right? Yeah, because I take the function of the eigenvalues, right, instead of the function of the operator, garnished by the projector on associated with the respective eigenvalues. Okay. Also in the back, you took notice. I mean, those people who stood, did you stand long enough? Okay. Here. So now maybe just for the mathematically more interested. So now why do we have a guess why for deriving this here the defining property of the projection operator is important? We have a guess why this is important. If you look now this form here, right? And I said that F typically has to be Taylor expandable, so it has to have a series expansion which converges, right? So do you have a guess why then, where this proof the projection, the property of the projection operators becomes important? Look, I said that F is Taylor expandable, right? So now what concerns the eigenvalue here, I have a Taylor, I can conceive this F of Ej as a Taylor series given in powers of the Ej, right? So therefore, I would expect that in principle, I would also, when I do that, when I start here, right, take this power expansion of F, formally given in terms of A, I get powers of A, right? Which has scalar parts maybe, but then you have the polynomials, say, which is always A to the power something, right? But since A is given in terms of B's, right, and powers of J always give just J, right? That's the reason why here you don't have powers of complicated powers of the polynomials of the projections, but just these projections themselves, right? So there, it's a very important property, and the projection operator property is important to derive this result, right? Because otherwise it would be much more. Okay, this is really something. This you should hardwire. When I wake you up in the morning at 2:30, right, and I say spectral theorem, you should immediately say it, right? So that's one of the things really have to know. Okay, good. So now we want lost time.
Okay, so we have 1 hour. That's fine. Yeah.
Do you want a break in between it, Augustine? No. So now, okay, good question. So now, could you repeat the question in a way that everybody hears it, please? All have strong voices, so please do it. Look, the density matrix is an operator. So therefore, and it's a self-adjoint operator. What else is it? It's self-adjoint, but which other property does it have? On top, so to say. Look, what does the density matrix describe? Yes, but let's say, it describes the state of the system, right? But then, let's say, what's the meaning of the diagonal elements of the density matrix? Or if let's assume the diagonal, the density matrix. Excuse me. Thank you. Gesundheit, who knows that? What was you? No, it was not your voice. Somebody who knows German here? Anybody knows German? So here, so now assume the density matrix is purely diagonal, so all the off-diagonal elements are zero, right? So then what's the interpretation of the diagonal elements of the density matrix? So why do we need the density matrix, right? So far, you see, I'm writing everything in terms of vectors in my Hilbert space, right? So now, of course, formally, you can also consider density matrix as vector, but in a more abstract space, right? So, but let's say, now typically, the typical concept is that one has a Hilbert space, right? And there one has ket vectors, right? And at some point, then one says, okay, this object is not good enough. So I need something, I need additional more general objects, and then I introduce the density matrices. When do I need that? So, how much do you know about entanglement? Have you been trained already in entanglement? Yes? Who has been trained in entanglement? Please. Show up. Those who have been trained in entanglement, stand up, please. Give me another sign. Give me a sign. Okay, but a more visible sign. Otherwise, okay. So now assume you have a maximally entangled state of two qubits, of two spin-1/2 systems, right? So now what happens if you trace over either one of the subsystems? In which state will you find then the remaining state? So assume, okay, digression. Okay, so this I know this. So let's say. So now assume you have this state 0, 0 plus 1, 1, right? Psi equals, and still I need normalization, so I put 1 over L2. So now when I do a partial trace over either one of the two subsystems, what do I get then? What is the remaining state? So I trace out, I don't know, above, right? And then in which state will I find Alice? Yeah. I trace out, so I say I don't care about the state of both. So then again what? Yeah, but let's say if I measure, right? So if I measure on both sides, for example, I measure 1, right? Then I will also then if Alice measures, she will find 1, right? And if Bob measures 0, Alice will measure 0, right? But now I do a trade. Now I say, okay, I will only do measurements in Alice's lab, and I don't care about what the Bob does, right? So I just integrate 50/50 out. So I do a statistical average over the possible measurements of Bob. So then I look at the state of Alice. So in which state will Alice be then? I'm asking this because of Augustine's question. So will it be still a pure state? Will it be a pure state or will it be a mixed state? It will be a mixed state. And a mixed state, and will it be a neatly mixed state or a maximally mixed state, or what will it be? If the state is maximally entangled initially, so then the remainder of the state of the remaining subsystem will be in a mixed state, we said, but which degree of mixedness will it have if the state of both is initially maximally entangled? 60% of what? That's not a completely precise statement. So 50% will be the probability to find. Yeah, 50% will be the probability of finding either one of the two states in which the system can be, right? So this means the state is maximally mixed, right? Because I have, it will be a diagonal, will be a strictly diagonal density matrix with no off-diagonal elements, with vanishing off-diagonal elements, both entries, diagonal entries being 1/2, for 1 dimension, for a 2-dimensional Hilbert space, global Hilbert space. So this state in which this maximally entangled state, right? This maximally mixed state cannot be represented anymore by a state vector inheritance space, right? That's why you introduce the density matrix, right? And so therefore, the diagonal elements of the density matrix are probabilities to find a certain are just classical probabilities. Okay? That's why I was asked, right? So now, and since it's probabilities, and the original, you see, my original question was, okay, the density matrices are self-adjoint, but they have additional properties, right? And so now we said, okay, if density matrices are strictly diagonal, there are probabilities on the diagonal, right? So the eigenvalues are what if it's a probability? Where do the eigenvalues have to lie? Where in the complex state do they have to lie? These probabilities. Generally, in quantum mechanics, I'm dealing with complex numbers, right? So now I have, but now on the density matrix, through diagonal, I have probabilities on the diagonal. So where in the complex number do these numbers, which can sit on the diagonal of the density matrix, have to sit where in the complex diagonal? Very small set. Ah, there is Frank, yeah. Real axis, yeah, and where on the real axis? That's it. INJ, yeah, no, but let's say where on the real axis? Can the probability be negative? Ah, sorry. Okay, so it's sitting on a non-negative, it's a non-negative number, right? So therefore, you say density matrix is a self-adjoint operator. But it's on top, it's a non-negative operator. And a non-negative or a positive operator also, slowly speaking, right? It's an operator which has strictly non-negative eigenvalues. Okay. So the density matrix is self-adjoint, right? And it is non-negative. And then the density matrix also has a spectral decomposition, right? So this now I take the Hamiltonian, but since the density matrix is a self-adjoint operator, I can also write down this eigenvalue decomposition or the spectral decomposition of the density matrix, right? And your question, I think, was whether the density matrix is the spectral decomposition, right? But the strict answer would be no, because the density matrix is a self-adjoint non-negative operator, and it has a well-defined spectral decomposition. Okay. Okay, good. Okay, so that's mileage. Okay, so now, right. Okay, as I said, right. So now we know. Okay, maybe I'll give you a break. I mean, or do you still are you still with me? I think you are still with me, right? So I make one more argument and then we make a break. Okay. So what? Okay. So now we go back to our problem, right? This was the Hamiltonian. Okay. We know we have diagonalized this H0. We know the eigenvalues, right? And we want to know now how switching on this perturbation or this coupling changes the dynamics of this already known system, right? So, and we know that if D were 0, then the time evolution would be just given by this. If H0 is diagonalized, we have the eigenvalues, so we can do everything, right? For any arbitrary initial state which we can solve this problem, right? So, but now we switch on V, and now we want to know how V changes the dynamics, right? And so now, in principle, for doing this, what you have to do is to solve the Schrödinger equation. So we have to solve the Schrödinger equation. I write it like this: minus bar dt psi equals h psi. Okay, so now h equals h0 plus d, right? So the dynamics under h0 is trivial, right? So therefore, we want to go now to the interaction picture. So this is the Schrödinger picture, right? This is the Schrödinger picture. And so now we go to the interaction picture. Which has the purpose to isolate out, if you wish so, right? Only the effect of V, the net effect of V, without the trivial dynamics induced by H naught, right? And so I told you last time, or I asked you last time, please check or try to find out how this equation changes if now you define psi I. So the state, the solution in the interaction picture is given by e to the plus I H naught T over H bar times psi at all moments in time, right? Well, you see what this does, right? If now psi is given by psi at time t is given by e to the minus I H naught T over H bar times psi at time 0, right? Essentially compensates this term, right? So it compensates the trivial time evolution, right? And now who has done this? Who has tried to derive the new form of the Schrödinger equation in the interaction picture? Anybody has tried that? Anybody did that? No? May I ask which quantum mechanics books you are using typically? Ja, wir schreiben jetzt nicht aus. Quantum mechanics. Saskia? Yeah, okay. So, I mean, would it be interesting for you if I gave you a list of quantum mechanics books on the lecture notes or something like this? Okay, so I will do this. I will do this in the material, right? Okay. So now, okay, so let's try to do that now. Okay, then we take a break. Okay, so let's do the following. Okay, so we start from this here, right? So if I H dt, now replace this by this, so psi, right? I can write this as e to the minus I H naught T over H bar times psi I. Yeah, and then on the right hand side I have H naught plus V acting upon psi, which is again e to the minus I H naught T over H bar times psi I. Okay, so now the time derivative of this first gives me here, if I apply it to that, right, it gives me a I times minus I over H bar times H bar. So the H bar goes away, right? And I times I gives minus, and minus gives plus. So it gives me a plus H naught. H naught, correct, yes, times e to the minus I H naught T over H bar psi I. Yeah, and then plus, and now this applied to that, right? I H bar e to the minus I H naught T over H bar times dt upon psi I. Yeah. And now the right hand side is H naught times e to the H naught times e to the minus I H naught T over H bar times psi I. Yeah. Plus V times e to the minus I h naught t over h bar times psi I. Right, so now this and this are identical, they go away, right? So then what is left is I h bar times this exponential times dt psi I equals b times this. So therefore I can also take away the exponential. So what I'm left with then is I get I h bar dt psi I equals, no, sorry, I cannot do that. I cannot do that. Argument was wrong, right? Because let's say, I mean, to get rid of the e to the minus I essentially I have to multiply from the left with e to the plus I h naught t, right? And this does not necessarily commute with b, so therefore I get actually here. Let me see. Space. Put it here. Okay, so I get e to the I h naught t over h bar, right? I multiply from the right with e to the plus I h naught t over h bar times v times e to the minus I h naught t over h bar, yeah, times psi I. And now this I define, right, by defining this here as bi, right? I get bi psi I, right? So this, and I'll reduce that left hand side to make it more compact, is I h bar dt psi I. Yeah, so therefore the interaction picture, and then often you say the interaction picture with respect to h naught, right, is such that the dynamics is just generated, is only generated by the perturbation. Perturbation now redefined, right? I mean, the perturbation itself in the interaction picture, right? And so that's now the solution we are going to solve after break. Okay? We have seen that. We have seen that already. Yeah. You have seen it. So, and this is a very important equation, right? Because it makes your life much easier. Okay. So because let's say this means you do not have to carry away, I mean, all the dynamics, the boring dynamics which is induced by H naught, right? So this is an equation which you always use whenever you look at quantum systems which are exposed to some perturbation, right? And look, what is the perturbation in a quantum algorithm, right? In a quantum algorithm, so say in principle you have all the different qubits which would evolve under the local Hamiltonian. So each qubit has just this boring sigma z Hamiltonian, right? And if you were not coupling, then nothing would happen except this boring H naught dynamics, right? And now you couple them, and these couplings are terms in the Hamiltonian which corresponds to this B, right? And so therefore, then you ideally want just to see what dynamics, what the coupling does, how the coupling changes the uncoupled dynamics of your qubits. And that's of course everything on which your computing algorithm hinges, right? So now I see that there are some questions that there's something you cannot read. Please tell me. What can you not read? What's not clear? Just say. Well, come forward, Steve. So your name was again? Eric. Yes, Eric.
I'm trying to connect this as are we dealing with this already?
Okay, good. Okay. I have to use the micro, sorry. No, stay here to be clarified. So, look, this is my Hamiltonian, okay? So it's H atom plus H harmonic oscillator plus the perturbation, right? I took away that this sum, I define as H naught. This together, I call it H naught. Okay? So this I call V. Yeah. And now I look at the Schrödinger equation, this is the Schrödinger equation. Now I replace this h by this expression here, right? So now I get, sorry, what did I do there? Yes, so then I have, and then I define psi I as this. Now I multiply from the left with e to the minus h naught, okay, minus h naught here times t, which is this here. So I replace just this psi, which is sitting here, right, by e to the minus h naught t over h naught times this. This is this. And here I have the right hand side of the Schrödinger equation, which is h, right? And I just write h naught plus t, right? And instead of psi, again, I write e to the minus I h naught t over h naught times psi. Right? Is this clear? Yes. Right? And then I just operate with this on that, right? So now I get time derivative of this, right? Which gives me time derivative of this, right? It gives me, I essentially get minus I h naught over h bar as a prefactor, right? And minus I times I gives plus, right? 1 over h bar times h bar gives 1, right? So I'm just left with h naught, and then e to this, right? And then I still have to apply this to that by changing, right? And so I get this term, e I h bar e to the minus I h naught t over h bar times the derivative times psi. And then I take the right hand side, so I just multiply this out. So h naught times this plus e times this.
What's this?
Yeah.
Yeah, so, this part,
For the left side.
left side, so.
Right side. Okay.
Expanded each thing.
Just it's making extra sense, right? It's clear.
Then, yeah, this is mentioned.
This comes from the definition, right? So I just have to put it here, right? So I just have, let's say, I multiply this equation on the left with e to the minus I h naught t over h bar, which is the inverse, right? So I get e to the minus I here, and here I get 1.
This part is the expanded.
Yes, yes. Alles klar? Everything clear? The other colleague there too? Alles klar? Everything clear? What is not clear? Tell me. Please. Okay, good. So then we have a break and then we solve this. Okay? Fine? Good. So 10 minutes break, please.
So we start again at 12:15.
And if you have any questions, I mean, you can ask me during the break, of course. No, ask me after the break. Wow. Changing, right? So I have this product. This, and then I can do this about this. That's where. How develop this? Okay, you heard already that. I found that. I told you, this is a showing picture, right? Because here psi is just generated by everything. Now I want to have something simpler, or I hope to get something simpler to get rid of this area. Right? So I get rid of this by such a rules.
So like this one, the left side.
Yes, so I want to get down the picture for this. It's also, let's say, one interpretation is, let's say, have you heard about the Heisenberg picture? Yes, so what is the Heisenberg picture? So, the Schrödinger picture, time dependence is carried by the states and lessons. And the Heisenberg picture, time dependence is carried, as I said, by the operator. Right, so H now here, okay, so we are looking at our V, but let's say in our V, wait, no, in our V is not fixed, time dependent, so I keep it, so we can assume that V is time independent, right? So then you say, okay, so the operator is time independent, as a state. You also say if now we have no V, right? Then doing this actually means that now V is 0, right? I do this with psi. So
you need the any
so now if I take here H equals H, right? So V equals 0. So then let's say if then I have psi of T. E should have e to the minus 5 H naught T was H bar. So 0 and 0. Yeah. Right. Now if I do this, right? So then I just absorb this, right? So then psi I of T in this under this construction, then psi I of T so when you see that, you should imagine that now. Now, this psi, right, it is dependent on some basis, right? It can be quite something like this. So now, what does that mean, right? This state here is not the phase, right? The function. So then, let's say this dynamics next state, right? Basically, just consider this as a state, not state, or is observed, or consider by the so I can now you can do it as a small picture because of the state, but now you can also same thing can be described by doing this. I can also there's a bit and the picture means that this is fixed, right? But now actually You will change the coordinates. If you were to rotate your coordinate system, right, keep this fixed. Now the station after, let's say at a later time, so plus, so then you see that now, yeah, the eigenstate, the basis state changed, right? So you take the reference system. So and change it, and so this was means essentially you take the reference system to the extent that it's that dynamics generated, right? And then what is left this year is just the effect of this moving reference system, moving by this operation. B just changes the position. Yeah. So it's essentially a change of effect, right? Yes, either you keep the reference fixed and you just make a vector. Let's show you a picture. If you keep the vectors fixed and you make only the reference system fixed, then that's the Heisenberg picture. And if you move the reference systems by the dynamics given induced by H naught, but you move the state by the dynamics given by V, that's the interaction. No, Edward. And okay.
Okay, 2 more minutes and then we start. Yeah.
Das heißt, wenn in der Woche ist nicht der Stock rein, dann So I want to essentially I say we are not we have this, but it's just that this makes sense. So this is the critical so this one will by replace now by replace this one by Minus layer is not clear, but it's then I am keeping the minus layer, but it's not that's what it happens. I just had to say, right, it's not okay, it's not about me. I am again. Yes. Then what is motivation? That's the example. Of the Bibles in the I would say okay, people, we continue, please. Seatbelt, please. Ready for takeoff? Okay, so probably I would continue. When should I stop? 1 o'clock or what? When should I? 1 o'clock is fine. Yes. Okay, so there were some questions now. So let me maybe see the space. Anyway, so I leave it because otherwise yeah, most stuff which I need. So look, one question was now, for example, one question was, what is this psi I? Right? So the psi I is just simply, in some sense, it's a new object, right? It's an object which I define in terms of the actual wave, of the actual state, which is probably psi. But transformed by the action of this operator, which is e to the plus IH naught t over h bar. Okay. And so now imagine e equals 0. Okay, so now imagine we have this Schrödinger equation and h is equal to h naught. Right? So then I know that the time evolved state, let's say for any initial condition psi naught, right? Yeah, here, for any initial condition to solve this equation, right? Then the solution is formally given by psi of t equals e to the minus I h naught t over h bar times psi naught. Right? Correct? Huh? So now, if now I look at the time evolution of psi I rather than of psi under this definition, so then I multiply e to the minus I h naught t over h bar times psi naught from the left with e to the plus I h naught t over h bar. So what would be the result? What's the result of e to the plus I h naught t over h bar times e to the minus I h naught t over h bar times psi naught? What is the result? E to the plus I h naught t over h bar times the minus I h naught t over h bar times psi at time 0. It's 1 times psi at time 0. So it's equal to psi at time 0. Right? So therefore, if I take this definition and v is 0, right, then psi I doesn't move in time. It's just a constant, it's just a fixed vector. Right? And this means that, okay, so now what do I do? Yes, I need more space because it's too small for you there. So I take. Let's say in Schrödinger dynamics, so the usual Schrödinger equation, which you know, which is this here, right? There you have some basis state, let's say 1, and some basis state 2, just an orthogonal basis in which you represent all your operators, right? So that's your referential, if you wish so, right? And your basis states are fixed, right? But then, for example, it could be defined as the eigenstates of h naught, right? But now you have some state, some initial state psi naught, initial condition, right? And then what does the Schrödinger equation do? It just, involves this psi under this unitary evolution, and since it's unitary, the length of the vector remains constant. And so the time evolution is something like rotation in this abstract space, right? This would be psi at t, right? And this mapping is done by u of t. Okay? This is clear? Huh? So now you can do this, and so what is important now that after this application of u of t, your new state in terms of your basis state is essentially given by these projections here, right? Yeah, which have changed because the dynamics is non-trivial, right? So now, but you can also conceive this as essentially. And also, so that's also what people, that's the Schrödinger picture, or it's also what people call the active interpretation, active in the sense that the state vector itself moves, right? That's the state vector, right? I can also imagine that now, okay, the other picture would be the following. So here's again the psi of 0. Psi of 0. And now to get the same effect of this time evolution of this u of t, could keep this fixed, right? And instead you do something like this. You move your basis vectors. And then you see that now, as you move to basis vector, so this would be now u dagger of t, which is essentially this here, this plus 5 multiplication. Yeah, right? So now you see that again, after you move your coordinate system, also now you have these new projections, right? So the projections you really also represent the dynamics correctly, but not by making the vector move, the state vector move, but making the coordinate system move, right? And that's essentially what you do by changing the perspective by looking at the dynamics of psi I rather than at the dynamics of psi, right? So this would be this now in the absence of B, this would be the Heisenberg picture, right? The Heisenberg picture puts all the dynamics on the operators and of the eigenvectors, which define the referential or the coordinate system with respect to which the state moves, right? And the Schrödinger picture puts all the dynamics in the states. And so therefore, psi I is just a new object because we find it convenient to look at its dynamics rather than at the dynamics of psi. But we know that once we found the dynamics of psi I, since we know which is the relation, which is a well-defined relation, we can always also find the state psi of t, right? So it's just we just take an object which makes our life easier, right? Because then the evolution equation for psi I is much simpler than the evolution equation for psi. So therefore, we first change the reference system by replacing psi with psi I, find the solution for psi I. And once we found the solution for psi I, we can still go back to psi by just applying the original definition, the original relation between psi I and psi. Okay. And then there was one more thing which was also clear apparently. So look, then what I did, I mean, I have this definition. I start from the Schrödinger equation. I replace psi in the Schrödinger equation by the expression of psi in terms of psi I, which is e to the minus I h naught t over h bar times psi I. Because if I multiply this equation from the left with e to the minus I h naught t over h bar, I get 1 here, and I get this e to the minus I h naught t over h bar here. I plug this into the Schrödinger equation. I replace this by this on the left-hand side and on the right-hand side, right? And then I have a function, I have a product of two functions which depend on time. This here and this depends on time, right? And so when I apply the derivative with respect to t, I have to use the product rule. So I first take the derivative of this and keep this fixed. And then I take the derivative of psi I and keep this fixed, right? That's it. Now we come to the solution. Which will be a bit bulky, right? So I need to space now. And you find these calculations also in this material which I put on the Google slide. There, and I put in the comments on this PDF in particular in section 2.3, right? Right, so now solution. I dt psi I equals bi psi I with vi equals e to the I h naught t over h bar v e to the minus I h naught t over h bar, right? And the v given as in essence h bar g times a plus a dagger times sigma plus sigma dagger, right? And so now, right, so now this becomes a bit more complicated because if you now we have to unfold this h naught into the two terms h atomic and h harmonic oscillator, right? So therefore we get So for the solution, now we want to go explicit, right? So therefore we have to plug in the definitions here, which we had originally. So we get VI equals ETI H atomic times T over H bar, right? Because here that's the sum of H atomic plus H harmonic oscillator for the field, right? Times E to the I H harmonic oscillator times T over H bar times V, the original coupling Hamiltonian, which was essentially A plus A dagger and times sigma plus sigma dagger. And then E to the minus I H atomic T over H bar, E to the minus I H harmonic oscillator T over H bar. Right, and this now, I mean, for reasons of time, I will not do this calculation, which is actually a slightly more complicated calculation, but if you are, how should I say, resilient, right, you will do it, right? And actually, the details are given in this PDF I put on the Google site, right? So you do some massage this a bit, right? And at the end, you get following expression. You get H bar G. So now you need space. I will need the entire line probably, or at least, so A times sigma. And the A times sigma comes from the V, right? We recall that V was H bar G, A plus A dagger, sigma plus sigma dagger, right? So therefore, it's not surprising that now appear the different products if you multiply this out, right? You get A times sigma times the exponential of minus I times omega, capital omega plus lowercase omega times T plus A sigma dagger times the exponential of minus I times omega minus omega T plus A dagger sigma, so A sigma dagger sigma times exponential of minus I omega plus I here, plus I omega minus omega times T. Then plus, so the last one which is still missing is A dagger sigma dagger, A dagger sigma dagger times exponential of I times omega plus omega T. And then the curly bracket closed. Okay, and so far I did not yet use, I mean, we had said originally, right, that if we want to transfer the energy between both degrees of freedom here of the field and of the atom efficiently, we want to have this near resonance, this resonance condition, right? But this I didn't use it, right? So far I didn't say anything about the relative size of omega and lowercase and uppercase omega. But now we take the resonance condition. Now we consider the resonance. So now resonance condition. Omega roughly equal to capital omega. So now what happens? How are the different terms in this expression, this final expression for VI? How are these different? And maybe I should say one more word about before we ask this. Maybe we go back one step. So you see, you get this form, right, with these different terms in which are in products of A and A dagger, or A dagger with sigma or sigma dagger. And then on top, you get these exponential factors which are time dependent, right? And this is at least plausible that you get them because let's say here you have the atomic Hamiltonian, which brings in lowercase omega, right? If you take its eigenvalues, right? If you have it diagonalized. And here you have the harmonic oscillator Hamiltonian, which brings capital omega, right? You recall that the Hamiltonian was h bar capital omega times a dagger a plus 1/2 times the identity, right? So therefore, I mean, let's say typically you will have to calculate commutators between these objects, which have, I mean, here it has a dagger, and this has also a dagger, sigma and sigma plus, right? This has sigma and sigma dagger, and this has also a dagger, sigma and sigma plus. We will have to calculate commutators, but once you have done all this, you get these expressions plus these time-dependent terms, which come just from the eigenvalues of these unperturbed Hamiltonian, these of the unperturbed Hamiltonian, right? So that's at least plausible, right? And now what happens if you make now this this assumption here? What, I mean, which is the qualitative, let's say my claim is now that the interaction Hamiltonian in the interaction picture essentially will have two types of contributions. Two types of contributions in terms of their time dependence. So when omega is, lowercase omega is close to uppercase omega, what happens then to this term? The argument is 0, right? So the exponential is 1, right? And what happens to this term? To omega, yeah, so it's oscillating rapidly, right? So this term is oscillating rapidly while this term is essentially constant, right? So now we recall this equation here. Now, if you have this and you integrate this over time, right? Now assume that a and sigma are time independent, right? So then what happens to this if you integrate this function over time? What do you get when you integrate the exponential of this exponential over time? What do you get? You get 1 over omega minus omega times the exponential, right? And here you get 1 over omega plus omega times the exponential, right? And so you see this is a rapidly oscillating term with an amplitude after integration, which is small, right? While this is a slowly oscillating term with an amplitude which is almost divergent if you get with omega close to omega, which is reminiscent of the resonance catastrophe, right? So therefore, under the resonance condition, right, these terms are dominant. The terms with difference of the two frequencies are dominant over the terms in which has the sum of the both frequencies. And this leads then to the approximation. You just simply drop these terms. Okay? And this is then called, and this is called dropping these terms. It's called the rotating wave approximation, which is a very, very important approximation in all this business when you want to build the basic ingredients of a quantum computer. Right? So when you see the motivation for doing this originally was that we want to understand how the Hadamard gate, right, which is such an important gate, how this is implemented experimentally, right? And so enlightenment interaction, right? And so now we are at this decisive step where we say, okay, under the resonance condition, right? There is condition, right? There is, and so you can also say that in these terms evolve slowly. These are slowly evolving terms, and these are rapidly evolving terms, right? That's also what you call, it's the separation of time scales. Have you already heard that, separation of time scales? I just heard that today Thomas actually spoke about noise, right? So so when you want to do a quantum operation, so how fast do you have to do this quantum operation with respect to the typical time scale of the noise? If you cannot correct the noise, you have to be faster than the noise, right? So you want to have rapid gates, right? So that the noise cannot fit into your suit in some sense, right? So and for this you need the separation of time scales. So let me see. So under the resonance condition, you get a separation of VI into rapidly and slowly involving terms. Rapidly are the ones with exponential I omega plus omega t, right? And slowly, they are ones with exponential I omega minus omega t, plus minus plus. For the sign in front doesn't really matter. It's plus minus or plus minus. You see it always appears once with plus and once with minus. Likewise for the difference, right? But this doesn't matter. It's the time dependence that matters. And so there's a part time dependence and a slow time dependence, essentially a constant, right? And so the slowly evolving terms, they are dominant. Right? So they dominate dynamics. Right, those in the back, please, who don't see what is written down, please stand up. See, or come forward, or next one. So wait, this is next, no, yeah. So you see that? Okay. So, right, and then what we do now, so therefore now we just keep the dominant terms and we leave, and we drop directly oscillating terms. And then we set omega equals to capital omega equals to lowercase omega. So then we end up with a time independent BI, right? And this I will chalk down in the next step. So now, drop bracket terms, yeah, which is what you call the rotating wave approximation. It's also called an RW. I mean, in the jargon, it's simply called RWA. RWA. Yeah. To obtain the Jaynes-Cummings Hamiltonian. Now the Hamiltonian form. So now I take this was BI, right? Without any approximation before I applied, so to say, the resonance condition, right? And now if I do that, and I so BI rotating wave equals BI Jaynes-Cummings. Jaynes-Cummings, right, is then H bar G, and then so this term goes away because it's rapidly oscillating. This term is left, so I have A sigma Dagger exponential minus I times omega minus omega t plus A Dagger sigma exponential I times omega minus omega t. Yeah, and also this term goes away because it's also rapidly oscillating, right? And then now at resonance, so for omega exactly equal to omega, right? Then it becomes h bar g times a sigma Vega plus a Vega sigma. Then from time to time you also write, from time to time you also write this here, you call this omega minus, omega call it delta. And this then is the detuning, right, between the driving frequency and the atomic transition frequency, so that's the detuning. So, right. So this is now, I mean, to be precise, Jaynes-Cummings interaction, right? But since the Jaynes-Cummings interaction in the Schrödinger equation, in the Schrödinger picture, plays the same role like a Hamiltonian, call this the Jaynes-Cummings Hamiltonian in the interaction picture. But divided, you always go into the interaction picture because you're interested in this non-trivial dynamics, which is in part infringed upon the system by the coupling to the coupling of the atom to the field, right? Near resonant coupling. And so now maybe let's go a little bit back to this term here, to this form before we have the rotating wave approximation, right? So now you see, you can also argue a little bit in the following way. You can say, okay, what does the subsequent application of maybe we need a picture. Yeah. So can I take this lower part away? This part here, this resonance condition, this can I take this away? Yeah. I want now to interpret. I want us now to interpret a bit the these terms which appear in this interaction picture, interaction Hamiltonian, before we do the Jaynes-Cummings approximation. So, I mean, let's say we know our system, right, is a two-level system. Yeah, and now I write a tensor product for 2 degrees of freedom, right? So it's a Hamiltonian of the atom and the Hamiltonian of the coupled of the quantized field mode, right? And so essentially, I'm acting with this VI, right? I could now, if I write this as a state vector, right? This VI acts on a state vector, which is actually can be written as maybe a coherent superposition of eigenstates of the unperturbed two-level system and eigenstates of the unperturbed harmonic oscillator. So now, what does A and sigma now assume I have such a state? So my state is now right like this, right? So these are just different ways of writing a state. So now, if I acted with A sigma on this state, what would happen? Where do I have to put the small black spheres now? So what happens if I apply A and sigma on this state? And I leave away now the prefactor. I was just which states do I end up with? Projections. So I act with the annihilation operator of the field and of the atom onto the state which has one excitation in the atom and one excitation in the photonic space. Winner, yeah. Now I can hear you. Down. With what? This goes down? Yeah. There it is. And this? Also down, right? This. Okay. So now I have this, but now is my dynamics unitary or not? Dynamics. Is the dynamics under which the state vector evolves unitary or not? Who is in favor of dynamics? Who believes that the dynamics is unitary? Who would bet for the dynamics being unitary? I mean, abstentions are not allowed now. Now you have to decide. It's like you have to vote for something. Who votes for unitary? Okay, 1, 2, 3. Who votes? Who votes against unitary? Outstanding, which is not allowed. Okay, so look, the dynamics is the dynamics, right? Was essentially the dynamics is still generated. Dynamics is still obtained by e to the minus I h t over h bar. Now we somehow, I mean, we transformed a bit to different references, right? But still we have Hamiltonian, Hamiltonian, which generates dynamics, right? So therefore, energy is totality of atom and field is conserved, right? So but now looking at that, is this energy conserving? See that this is not energy conserving, right? Because you have, let's say, you lose 2 quanta, right? So you lose energy, right? So therefore, therefore you would say that this term is not energy conserving, right? And now what about this term? Is energy conserving or not? Who votes in favor of energy conservation? Who votes in favor of energy non-conservation? Right. Okay, so because here you get 2 excitations, right? From nowhere. So therefore it's not energy conserving. Right? So the only terms which are energy conserving are actually this one and this one, right? And so therefore in quantum mechanics actually you say, I mean, you may have energy non-conserving terms, but they are only in what you call virtual transitions. They only induce virtual transitions, right? So typically they are in perturbation theory. At least you can see that they are subdominant, right? So that's another line of argument, right? So, but I brought it up, right? Because this, just to tell you that this is another argument which you find in the books, right? How to argue these rapidly oscillating terms away, right? But it's also something which tells you now about this, what we are left with when we have the James-Cummings Hamiltonian, right? When you have the James-Cummings Hamiltonian, we have conservation of energy which is manifest in the operators, right? Because if, I mean, omega is close to omega, if I win one quantum in the field and I lose it in the atom, I don't change energy and vice versa, right? So therefore, now we do something like this. So look, this is now coupling between the field degree of freedom and the electronic degree of freedom, right? Now I need somebody to throw something at me, please. Get something there. Yeah. So this excitation. So the excitation is going forward back between the 2 degrees of freedom. So I know excitation, right? So by the principle, so you see. So you lose the excitation, right? Okay, so I lose the excitation, he is excited, right? And now he gets back to me, right? And I get excited, right? And so that's essentially what's done now. You can imagine now the coupling between the 2 degrees of freedom like a ping pong play, and you always shuffle one quantum forward and back. Okay? And that's what this Hamiltonian now qualitatively describes, right? Now we will try to understand how this manifests explicitly in looking at our observables, right? Let me now just see how we are in time. Well, I think then I think there will be another session this afternoon, and then we do it this afternoon. Okay, now I wish you a nice lunch.
All clear? Yeah.
I didn't, they are now supposed to lecture to the first team up.
Yes, observer. Yes, observer. No, I will try. Can you write it, please? Just observer. Okay. So you don't say B, you say one, right? Just observer. You say B, just observer. Okay. Yes. Yes. I mean, let's say in the ideal world, not, right? In the real world, yes. Right? But depending on the noise is, let's say, depending on what if you do it well as an experimentalist, you can arrange situations such that it experience noise, but on only a very slow time scale, right? And so the purpose of this, what we are doing here is actually to make, I mean, to allow for gate operations, right? Which are so fast on the atom, right? So on the qubit, right? That this happens before the noise is really getting manifest, right? Yeah. You have read it, read it. Very good. You have looked at it. Yeah, very good. Yeah, very good. Yes. Yes, I mean, let's say, I mean, this is a very long discussion. So depending, I mean, the atomic physicists would say we can do it, right? And the solid state physicists would say we can do it, right? And the politicians would say we can do it, and the others not, right? And so far nobody did it. But but all of them can work with a small number of qubits. Yeah.
So that means that this has not been realized.
Yes, there are such things which are being realized, right? But the problem is, let's say, if you have just two qubits, it doesn't help you a lot, right? Or one or two qubits. I mean, for computer thousands, right? That's the problem.
Has anyone ever tried to
Yes, people are doing this. Yeah. Now people are trying to do hybrid architectures. So just you are a student here in Tunis, where are you? In Nigeria. Oh, okay. Which city in Nigeria? I don't know. So I just know. Wait. There is. How's it called again? You're from? I don't know the geography of Nigeria, unfortunately. We have a student in our master department who's in the PhD who was in Nigeria. Okay, great. So that's good question, right? So let's say in real world there's always noise, right? And so therefore what you have to do, you have to try to induce unitary dynamics, right? Which is faster than music. That's all the game. That's the good of the game, right? And also people try to, simply merge these different platforms, right? Ions, neutral atoms, photons, right? But the main problem is the scaling event.
So, measurements, you know, supposed to help, like, help with the
Whether it's possible, that's the question.
Yeah.
I mean, this is dependent. Look, I mean, I say you get very strong statements from IBM and from Google, etc. All these people who want to make cash, right? They make very strong calculations, right? They make strong claims, right? While if you talk to people who are really proper scientists, right, they are much more skeptical. Right? They also more honest because they don't directly profit from stocks and so on. So therefore, I mean, typically what's just very difficult. I mean, I say, of course, you can build machines, right, where you have many qubits, right? But then it's still very difficult to have all these qubits really coherent for it. I mean, it's very difficult. And the bet, I mean, let's say the open issue is whether this will ever be possible to really, protect the coherence of this large amount of qubits, or to achieve it and protect it and to use it, to exploit it in the computer. I mean, that's an open question. So now those who are apologetic of the content of the story, right, they would say, it will be done. Right? They say it will be done in 3 years, right? But they tend to say this for many years. Others are more skeptical, but I think the question is essentially open. Okay.
will come up.
Hello, sorry for the delay. You can go for lunch. The usual place, P22. P22.
Okay. One, two. Okay, welcome back. And now I just want to repeat with you what we said for a measurement before, before we left it. So what is the abstract description of this spinor half measurement? It's a spin, this property of in z direction spin up or spin down. And then I go now to the physical way to describe this. So what does the machine look like? The experiment that was first done, what did it look like? In order to understand how this is actually measured. And from there, we can then talk a little bit about the rules of the game. So what are measurements like? No, I mean, we can then make it again a little bit more abstract. So take a step back and generalize what kind of measurements we think they are. All right. So can someone tell me for a measurement, quantum measurement, there's two things I need to know. So first of all, I need an observable. Okay. So my observable in spectral decomposition. We heard from Andreas how interesting and what the spectral decomposition is. An operator. So this is an operator that represents the observable spin in z direction of spin halves. And it looks like this, h bar half, 0, 0, this is a projector onto one of the eigenstates, minus h bar half, this is an eigenvalue, this is also an eigenvalue, and then the projector onto the second eigenstate. All right, so what do we need to know of this quantum measurement in order to describe its physical properties in the abstract way? There's two things we always ask in a measurement. Can you help me? What would you ask now? If I tell you I have state, I get my state, okay, state preparation, and now I make this measurement. Right, and the state preparation, I know the state that I prepared was the state C0, 0 plus C1. So, what would you like me to tell in terms of the measurement? Someone help me. What is the two things that I need to know? I mean, I make a measurement of the thing, and how many values can I get? 2, right? H bar half and minus H bar. So one question could be, which value can I expect? I mean, what is the value that will be coming more often, or maybe will only come, or something like this? Okay, so that speaks to which quantity. What describes the appearance or the relative frequency of how often things appear? I need to add for that. It's the probability. Okay, so you have to know what is the probability for. So this is the first thing. What's the probability for the measurement outcomes? Let's call it plus and minus h bar half. Plus minus h bar half. This is what you have to know. And in our case, let me just put it plus h bar half would be the expectation value of phi 0 or phi with respect to this projector 0, 0. So we said this is equal to 0 phi model street. Okay. And it was in our case. And then the other probability, second, sorry, it's not second. This is the one probability, and then the other probability is correspondingly the expectation value of the projector to 1. Right? I call this an expectation value because it has here a phi and there a phi. The middle is operator. And this is equal to C1 squared. Right? So that's the one thing. And the second thing that I need to know, so you must tell me with what probability does each measurement result come. And the second thing you want to know is what's the state afterwards. Okay? So what is that state afterwards? Well, I said, or we said that it depends on the measurement result. If it's plus h bar half, then we go to the projector onto this that corresponds to this h bar half psi phi. So it's projected onto the eigenstate of the thing, and then we have to normalize it, which is the square root of this probability of plus h bar half. And we found out this is equal to 0. So it really projects onto, so this projector here, by the way, what I mean by this projector is dh bar half is nothing else than this projector onto the eigenstate that corresponds to spin half. Minus h bar half would correspond to 1. Right, so we get from this, we get this, and for phi going to minus h bar half, we get p minus h bar half phi divided by square root of the probability for this result, and you would get 1. Okay, so that's what we did last hour. And now I'm going to tell you how it works in reality. Okay, so this experiment that I'm going to tell you about was done in 1922. Okay, and that's more than 100 years ago, 104 years. Right. And basically what happened there is the following. So we have, you can't see here, right? I better put it here. So we have an oven, okay? An oven that is something that heats something. And inside here, there is silver atoms. Okay? And silver atoms, they have a certain electronic configuration. And it happens that they have only one valence electron. So they have 4 shells that are completed with electrons. And they are more or less not neutral. Okay? They don't have any spin. But the AG has one valence electron, and it is in the 5s shell. Okay, so 5s. Sorry, let's write it like this: 5s, and then there is. There can be 2 electrons, but I think this one is in cluster R. Yeah, no, that depends. Actually, degenerates. So it could be in S a half or minus a half. Plus minus. Right? So that means the magnetic spin quantum number can correspond to plus a half. Mu B, which is Bohr's magnetron, times H times. No, that's it. And so plus h bar half, sorry, and minus h bar half, that's the 2 things. So basically we have a spin a half system because all the electrons in the lower orbits. So until the shell 4, 3, and so forth, only they are neutral, but only in the 5s shell. 5s, there is 1 electron, okay? And this has a minus sign, and it's a spin a half party, okay? So it's spin a half. So now these electrons, these atoms with the electrons, they come out of this oven, and then they fly through a magnetic field, and it's an inhomogeneous magnetic field. I'm trying to draw a magnet that has, so this is maybe, like the plus pole. And then here we have a thing that is a different form. Okay, so this magnetic material, and this, in this case, positively charged, it means maybe minus. And then there is a magnetic field that points in this direction. Right? So in this magnetic field, what happens is that the electrons, so everything here is neutral, but the total spin of the thing is a half. So, you fly through here, and then there is energy that depends on the magnetic moment of this 1 electron you know, I mean, the electron is basically spinning, no? And if you spin and you are charged, then you get a magnetic moment. No, if you have a current that goes around, then there is a magnetic field. No, it induces a magnetic field. It's just this is just the laws of Maxwell, right? And this magnetic field, so Faraday's law, and this magnetic field is proportional to the spin. Okay, so there is a magnetic moment that is somehow a function of the spin, and there is a magnetic field, an external magnetic field. This is dot product. Okay, and if both the magnetic moment of the electron and the magnetic field are aligned, external magnetic field are aligned, then that's perfect. That has the lowest energy. If they point in opposite directions, this has the highest energy. You can believe that, right? And so therefore there is this minus sign. So if they are aligned, then I get something big out here, and with a minus sign, I get something very small, and then so negative. And then if they are anti-aligned, then this is negative, then I get something positive, it's higher energy. The Hamiltonian is the quantity that the observer that describes the energy of this. All right. And now it looks like this. Okay. So now I have to just say what this mu b is. And I can tell you this. So this mu is proportional to the S. Okay? S is the spin of this electron. And the proportionality constant is mu b, okay? Which is which looks like this. Okay. Mu b. This is Bohr's magneton, okay? And it looks like this. I think it's we have a h bar here, okay? Then we have a 2 over the electron mass, and I think we have the speed of light here somehow, at least in certain units. And then we need the electron charge. Okay, so this is the elemental charge of the electron, but it's given in positive. So it's just the magnitude of the charge, and then we have again the S. Okay, so let it be this. Okay, so this is the quantity that makes the electron, the magnetic moment of the electron. And you see it depends on the spin. Okay, so now what happens in the field? So basically, maybe I should write down what this B does. So B is a magnetic field that has a gradient. Okay, gradient means it's not constant. It increases along the z-axis. Okay, so this is the z-axis. This is the z direction, and in this direction it flies, maybe the x direction, right? And this thing here looks like this. Let me see what I noted down here. I said this is B0 minus P, some constant times Z. Where Z is this, let's say Z starts here. Z is this Z component. It's just a reference frame. And now the thing flies through here. And while it is in this magnetic field, the thing that has spin up gets accelerated. It takes some momentum in here. There is a force that acts on it. If you have something like this, and this is like a potential, and if you take the derivative of the potential, you get the force, and the force points in positive z direction, given that this thing here is big enough, and then you get accelerated up, okay? And then there is another, so if you, this is for spin up, and for spin down, you get accelerated down. Okay, and then you hit some screen. Okay, so here's the screen. Actually, the screen in the original experiment in 1922 was a glass plate. They just used the glass plate. Okay, and on that glass plate, they looked at little impacts, little hits. You know, so if an electron would hit the glass plate, there was something like a small dent or a small crack or something like this. Not for all electrons, but for some. Okay, and then they looked with a microscope at this glass plate to see where the electrons had pinched in. So it's actually not electrons; it's the silver atoms. So the electrons would make much less of an impact. But in silver atoms, they have some kinetic energy that means hitting the trace of the hit. Okay, so just to give you an idea about the dimension of the thing. So this is spin up, this is spin down, and to give you an idea of the dimension, what they saw here. This is now in Z direction again, and this is Y direction. And what they saw was like two lips. So a small thing that showed all the traces of electrons of silver atoms that went up, okay, and then a similar thing with those that went down, right? And the distance between the upper limit or boundary of the upper lip and the lower lip, this was a distance of 2 millimeters. Okay, so it's not far apart. You really need the microscope to see this, right? And the distance between the inner lips, so between here and there, so this distance here was, let me just check, it was 0.11. Okay, so this is tiny, the thing, right? And they somehow thought, they called it a direction quantization of direction. They thought if we fly these atoms through the magnetic field, then something strange happens, and they either have to go up or down. They never go straight. Okay? That's why they thought this is a quantization of the direction. But they didn't know about the spin of the electrons, and they didn't know about the magnetic moment. But if someone would have taught them this, the magnetic moment, they would have understood it. Then they would have said, okay, maybe it's the spin that is quantized. And really, the spin is quantized because it has only two values, either plus h bar half in the Z component or minus h bar half. Why do I talk about the Z component? Because this thing here is in Z direction. Okay, so maybe I should have written this here. This is, let me call this, I call this EZ for unit vector in Z direction. It's not, so the E is for Einheit, which is the word in German, but it doesn't matter. So this is a unit vector in Z direction. And then, if I take this, this EZ and I have this dot product here, then I see that H is actually equal to minus mu Bohr, okay, minus mu Bohr times SZ times times SZ times this. Okay, let me write it in front. So E0 minus B times Z, and then SZ. I might have made a mistake. Let me just check it. Yeah, I made a mistake. Maybe this is not quite true. This is just the mu Bohr is just E over E over MEC. Der minus sign, there is minus sign, also minus. And then this SZ gives me H bar half, so I get minus E H bar, and then 2 MEC, and then a sigma Z, where a sigma Z is not a Pauli matrix. Okay, so sorry. In fact, I have to write here 3 Pauli matrices: sigma Y, sigma X, sigma X, sigma Y, and sigma Z. And then, if I have this thing here, then I just get the EZ. So these 3 components, they are matrices because they correspond to the quantized observables. You know? This thing here also I can write as H bar half sigma Z. Okay, check it yourself. And then I have here E is should have written this UV. I didn't like this. Let me take this away. I'm sorry for this. Let's put it like this. And then we can write this thing here as mu B. And then it's not so complicated. So now this is equal to mu B. Let's leave it here. I write it here. Mu B, and then I can replace this by just sigma Z. Then everybody's. I think this is correct. Let me check. Mu B sigma Z. This is correct. Okay. So, is it a minus sign? No, this is a plus sign. Together with the minus here, I got here plus. All right. So this is the case. Okay. So we can check again the coefficients here, but it's of this form. So it has 2 operators in there. This is an operator or a matrix, and the Z here, it looks innocent, but it's also operator. Because we are dealing with the Z of the Z component of the position vector in an atom, and that has that is an operator. Okay, just like this thing here is an operator. In quantum mechanics, all the variables become operators. Okay? But we'll see what that makes, what that does. So we are not worried. Not worried. It's always super simple. Okay, so this is the physical thing. And of course, what you see here is that if these lips are really kind of separated, then everything is fine. I can say if I find the electron, the impact above this 0 line, then everything is fine. Then I get spin up, and I've measured spin up. And if I find it below here, then I measure spin down, right? And then I can use this description actually. I can say, yeah, let me see. I want to know what happens here with the state, you know, with the state. And I just check. I now send many atoms through the thing. And I find some of them here, and some of them I find here. And what would you say? What is the proportion of atoms that I find here on the upper part? How is that proportion related to these coefficients C0 and C1? What do you think? Serious question, okay? Because we calculated the probability to measure, to project onto this eigenstate, which is the eigenstate that belongs to H bar half. So we calculate the probability for H bar half to be this value, okay? Let's say this value is 3/4, okay? What would this value be if this is 3 over 4? What do you think? What's C1 then? Why? I mean, they have to add up, you know, these are probabilities. Either this happens or that happens. So the probabilities have to add up to 1. So I'm looking for the counter probability to 3 over 4. 1 over 4. Okay. So let's say this is so. Probability to get h bar half would be 3 over 4. Probability to get minus h bar half is 1 over 4. So how many atoms, what fraction of atoms would I find on the upper limit? You don't know? I mean, you know, we must now connect the dots, you know? We must connect the point that if it spin up, I said this, you know, I haven't proved, but I'm gonna prove, okay? But I said that what they observed, Stern and Gerlach, was that if they put in only spin up, so let's say C0 is 1 and C1 is 0, okay, then they found only atoms in the upper half, on the upper limit. And if they put in only atoms that had minus a half, so h bar half, minus h bar half, then they would only find them on the lower limit. So that the ones that have spin up, they fly up. Ones that have spin down, fly down. So if I have the situation now not with 1 and 0, but with 3 over 4 and 1 over 4, what do you think? How many of the, let's say I send 100 atoms, how many of them will I find on the upper limit or on the upper half of the screen? What do you guess? How much? 25? Who says more? How much? 70. Okay, now we have the choice between the 25 and 75. Well, this is 3 over 4, so that corresponds to 75%. If I send 100, it's 75. Okay, so 75 of them I will find here, and 25 there. So that would correspond to your measurement statistics. You understand? So this is a very nice description. But I mean, how do I get that out of this process? You know, I mean, I just said it is like this, but maybe you don't believe me. I have to somehow calculate this, right? And I want to go with you through the calculation just once, because it gives you a sense for what happens. I mean, what happens to such coupling? If I have here Z and sigma Z, the Z is observable of the atom. It's the position of the atom, actually center of mass. The atom is more or less the nucleus. You know, the center of mass is in the nucleus, right? So where on the Z-axis is this atom? That is the question I want to find, because that's where it's going to land. Is it going to land here or there? I'm not so much interested in this y direction. Where is it going to land? Because the Z direction decides whether it's spin up or spin down, right? So now let's try to calculate that together. How do we do that? This is the question, right? So basically, yeah. So what is the suggestion how we do this? So how did Andreas do this? I mean, he also had a Hamiltonian. Then he wanted to calculate some time evolution, right? Can you remember how he did that? So how do you get the state of the system? So first of all, what is the state of the system? Maybe you should say that first. The initial state of the system. I call it psi 0. So this initial state is the state of the spin, okay? But it's also the state of the center of mass of that thing. So it has some kind of wave function, right? So how do we write that in our language? We write this as the spin state. Let me see where I put the spin state in front. And no, I put the spin state behind. So first I have the psi of 0. So this is a capital psi. This is small psi, and this is the center of mass state. Where is, you know, if I look at the wave function, so psi of 0, psi of x. Okay, psi of x and 0. And I take the model squared, then I might get something like this. If we put this as z direction, because that's very interesting. So this is the z direction. The initial thing that comes out here, you know, it might be like a wave function. You know, it might be like a Gaussian wave function. So most of them are in the middle here, a few are further out, you know, and that's how they fly. Okay. So this thing here, now, how is this was squared? How is this thing, how is this wave function related to how is that related to the let me make here a general position x. How is this related to this cat? This thing. You know that? How can we relate this to this? How do we get from this this? Anyone knows that? Well, we just have to take the inner product of the state where the thing is localized with the wave function. Okay, so this is the relation. If you know the Dirac formalism, you can get any representation. It's the representation of the wave function that's just called the position representation of the state. There's also momentum representation, which I will talk about in a moment. Okay, so this is the full state is just given in terms of the thing, and this thing is a vector. Let's not hit ourselves. It's a vector in an infinite dimensional space. That's a space with infinite many directions. Okay, this is maybe new, but it is a vector. All right. So now I'm going to write here behind there our spin state at time 0. And this is something easy. This is just in a 2-dimensional space. This thing we know. Okay, this is a vector in a 2-dimensional space. This is a vector that is a vector, but it has infinitely many points. So it's a little important, but not much. In fact, you can write this psi of 0. So for the center of mass, you can write it as the integral of this sort, right? Where here is the wave function. This is psi of x and 0. And this thing here is the state of the system if it's located in one point x. Okay? So basically you make here something, this is also known as the wave function. Okay? You make a wave function which is like a mapping that puts to each point in space a complex number. And if you take the modulus squared of this complex number, you get the probability density to find it in that point. Okay, so it's made out. It's a superposition as if the wave function has in each point in space like a basis vector, you know, a state, and it's summed over all. It's a superposition of being in each state, in each point. Okay. Everywhere where this psi of x and 0 lives. Of course, it doesn't live everywhere. You have, for example, this wave function here at 0, okay, psi of 0. This point, this wave function doesn't live over here, and it doesn't live over here. That's more or less 0, okay, but it has some non-zero values around the opening of the hole. All right. So until there, I've now painted my pictures. and the picture, and now you have to ask me some questions. Okay? Then I try to calculate for you what happens to this state. So this is the initial state. By the way, see here, I have a product of two states. Okay, this is sounds a little bit strange, but this is how we account for a system that is made out of two components, of two subsystems, namely the center of mass motion. The center of mass is one subsystem, and the other subsystem is the spin. Two components. And you just write the vectors, the bra and the cats behind each other. This is how we do this. In principle, if someone knows, has ever heard that this is two vectors, and it's a sort of vectors. But we don't have to worry. Because the rules are super simple. So we don't need to think much about it. These is never it's very simple. I just write it behind each other to keep track of course. Okay, so this is this. Do you have any questions? I know it's after lunch and I'm also tired and I don't know why I do this. But it will make sense in a moment, okay? Hopefully. And it's good that we have seen that ones. Or still the physics, why not? No? Okay, questions? No questions? Not at this moment. And this morning we have so brilliant questions to me. That one of the questions that I like most, and I want to know who asked it, was the question, how does the information travel back to the source and then in the other direction? Or how does it go from the Alice part to the Bob part? I really like that thing. It was fantastic. Yeah, a good thing to think about. Right. So now what we do here is what Andreas always does, and what I also do, and all physicists, we calculate the transition from psi of 0 times 0 to psi of t using a time evolution operator. And this is usually a unitary operator. Okay, so how is that done? So we write psi of t, and this, I mean the capital psi of t, that means the composite system, center of mass of the atom, or the atom and its spin. In this way, we write here u of t, psi of 0. Okay, so this is what we write. And can someone tell me what the U is made of? It has something to do with the Hamiltonian. How do we write it? Yeah, right. Be correct. So I need to the right answer is it's an exponential of the Hamiltonian, right? So it's just like when what you saw before, it goes like this, up to the minus I over h bar h and then t. Okay, let me call it, just because I don't think it's a very long time, let me call it dp. Delta t if you don't want it. And by delta t, I mean just a very small time because flies rather fast. Let's say flies at the speed of sound. All right. So this is the u of t, u of delta t. It's this. Okay. So now we have that, and we have to act with this thing, which is an operator, this H has an operator. That's what we have to do. And Andreas said this morning we have to do it best we go to spectral decomposition of the spectral representation of the H. Okay, yeah, we can do that first, and then we calculate. Okay, Let me do it for you. Okay, so maybe I'll delete this now because then I can start on top again, and then the people behind can also see something, right? If I go further down, then we don't see anything. Let me just take 2 words. Yeah, please make a photo down. But I also take one for good measure. Okay, 3. And yes, so. All right, so we have this, and now I'm going to clean the board, and then I do it from start. Okay, let me first go into the spectral decomposition of just the second one. So psi of delta t is equal to, I leave the psi for a moment, the position part. Let me just leave it, psi of 0. And then what's the spectral decomposition of this operator, I have to ask. Notice H has a part, H has a part that belongs to the spin. It's here, huh? Sigma Z, right? So what's the spectral decomposition of sigma Z? Okay. Can we write it down in terms of our basis states? Do we know it? Again, let us remind. Does someone know sigma Z? Do you still remember what it was? Yes? It was in 0 and 1, right? Okay, so it had the eigenvalue +1 with respect to 0, the eigenvalue -1 with respect to 1, and the h bar we somehow pulled somewhere else. Okay, so instead of +1 h bar, we have +1. Right, so this is the thing, and now I'm going to write it in spectral decomposition. I'm going to write it in the eigenbasis, and that is what we had already. So this is already in the eigenbasis. How nice, okay? And for this one, I'm going to make a trick because I'm going to play a trick. I'm not going to eigenbasis like Andreas would have done maybe. The eigenbasis of the set is the position eigenbasis. So it would be exactly this thing here. I would go into the wave function basis, where I can write everything in wave functions. But I don't want to do that because, how can I say, then it's difficult for me to show you what the Z, which is the operator, actually does. It would just multiply the wave function with a Z, and that is not very instructive. Okay. So I'm going to go into the momentum eigenbasis. This is a very interesting thing. So I can write the identity in this form, E3P P. So what I used so far was the resolution of the identity with the positions. Okay. So sorry, this was X,
Okay, so I can take this identity doesn't change anything. I can take this identity and multiply it in front of this thing, and I will not change anything. In fact, what I get is just a basis transformation. For example, if I take the identity in terms of the position eigenstates and put it in front of the center of mass part, then I get exactly what I have written down here. You can see this thing here is basically psi of 0 multiplied with this identity. Then I get this, right? And this thing here is just expressing everything in the basis of position eigenstates. Here's some coefficients and there's the basis. And it's an integral, so it's a continuous basis, right? And the same thing will happen if I put this identity in front. So is someone brave enough to tell me what I have to write here? If I put this identity in front, so identity psi of delta t. Okay, let me write it like this, sorry. Identity of psi of 0 times this other state, C0, 0 plus C1, 1. Okay, I'm gonna delete this. Okay, so what do I get from this identity? If I take this expression, I get the integral d3p, and then I have to write down the p. Okay, and then I have to write down another p, right? And now I have to write down the psi of 0, and the psi of 0 is like this cat, you know? But this cat hits this part, and then I get the inner product. So I leave one of the lines here out, and then I have just this. Yes, everybody happy with that? And this thing is called, the wave function in position representation. Okay, instead of in momentum representation. Instead, so this is the wave function of the atom in momentum representation. It's just a different basis than its position basis. Okay. So now, if this is the case, I mean, that was just the psi 0 part, and then of course I still get the other part. And now I want to let this thing here act on this. I'm actually going to, this was the psi of delta t. Okay. Yeah, there was something wrong. There was a u here. Sorry that I messed this up. This was psi of delta t. This was actually psi of 0. Okay. This is just psi of 0. Okay, but I want to actually calculate psi of delta t. So let me do this. Psi of delta t. And now I know this is u of t, delta t. And then psi of 0 and phi of 0. So going backwards. This was phi 0. Going forward in a second again. Phi of 0. And now I'm going to put the identity in front of it. So I write the identity here. Doesn't matter where I put the identity. And then I have the following. I have integral d3p. Sorry for standing in the way. P e up to the minus I over h bar b0 minus bz sigma 3 delta t, and behind there is now the psi of 0 and phi of 0, phi 0, right? And now I can expand this because, now the thing is, I know that this part here acts on this together with the Z. But I first need to know what's the sigma 3. And for this sigma 3, I really use the spectral decomposition. I write this in spectral decomposition, then I'm allowed to replace the operator by its eigenvalue. Okay? And then I just have in the exponent this operator, what I have to take care of, but this operator as well. Okay? And I will do that by letting this operator act on this graph. And you will see what happens. Okay, so let me do that. I now have two parts. Okay, so integral d3p p, then a big bracket c0 e up to the minus I over h bar. You know what? I have to, it's very funny. I have the wrong description. From the letter, right? It was here. So now it's P acting on E up to the plus I h bar. I know that's okay. There was a minus here, and the minus together the plus. So I want to actually, there's something wrong. I want to pull the B0 in front. B0 times delta t, I pull it in front. This is just a phase. Principle, I can forget that. But let me put it in front. And then I have P still. And then there comes P up to the I over h bar mu b times z times delta t. Okay, plus minus and minus gives plus. Okay, this is this plus here, and then I have the rest of it. And the sigma z becomes a 1 in front of the right state, namely in front of which state? Well, in front of the state sigma. Well, here is still something missing, namely psi 0, and then 0. Okay, and then plus, and now comes the thing with P, but with E up to the minus I h bar, mu b z delta t, and here is psi 0 and 1. Okay, let's try to understand what happened just now, because that's an important step. All right, so what happened now? What happened here? So what happened was that I wrote the phi 0. Oh, there is something missing. Here's the C0 here, but there should be actually this is not good enough. There is something completely missing. So this is the C0, and then I have why do I have a plus, a minus there, and a plus there? I don't understand at all. Do I understand this? The sigma z is in front of B0 and this. Okay, I understand this. Right, so that's great. All right, so what happened here? I forgot something. I have to write plus, then I have to write C1 because that's the coefficient in front of 1. Here I have the C0 in front of 0. Okay, so here I have let's put this back. 0, 0, and then plus. Then I say C1, and then I say E up to the minus IH bar B0 times sigma 3, but sigma 3 is replaced by the eigenvalue, and the eigenvalue in front of the vector 1, the spin up and spin down thing is minus H bar, right? Or it's minus 1. So I have to put in here E up to the plus IH bar, and then B0, and then delta T, and that's it. Okay, so here is the minus IH bar B0 delta T, because in the first component we have 0, and the sigma 3 is replaced by plus 1. In the second component, so in the component where we have a 1, we have to replace the sigma 3 by minus 1, and then we get here a plus IH bar B0, and here we get a minus. While at this point here it was the other way around. Okay, here we had the minus here and a plus there. Now we have a plus here and a minus there. Okay, everybody happy with that? What's going on? Okay, so this is the next step that I have here. You have a question? I think it's getting too much. So maybe we have to shorten this a little bit. I'm nearly there. Let me just tell you, we have to just go over one thing that we have to still understand, and then we are done. So what we still have to understand is the following. Namely, what does it mean if I have minus IH bar mu B Z delta T acting on a P? So if I know this, if I know what that means here, then I can also tell you what it means that that this thing here acts onto the bra. Okay, then I can then say, and the answer here is this: this position operator, the Z component of the position operator, is a translation of the momentum of the system in momentum space. So it adds momentum to the system. So what happens here is that this thing here is equal to P plus delta P, okay, where delta P is given by delta P is just mu B delta T, and there is a vector in Z direction. This has a vector sign. Okay. So what happens here is that I add something positive, given that V is positive, I add something positive to the momentum. Okay, so if this is the momentum of the center of mass motion, and I act with this operator, then I get a different momentum, eigenstate, namely a state with a greater momentum. Okay? And this is exactly this the momentum that the thing picks up in the homogeneous field. It moves in direction of the gradient of the magnetic field. Okay, this is what a magnetic dipole does. If you have an inhomogeneous field, it moves in direction of the gradient of this momentum, right? And in order to motivate it a little bit, we can think maybe of the following: that if you want to write, who knows what this thing is, dp over dt. What is that in classical physics? What? That's of course, that's correct. And you can also express it in terms of the Hamiltonian. Okay, so how do I express it in terms of the Hamiltonian? Let me make it a little bit easier. I just take the z component of the momentum. Then I can write this as minus dh over dz. Do you agree with that? Yeah. Okay. So if that is so, that means that dp, the increment in momentum, is actually proportional to minus dh over dz times dt. Right? This is what happens. And now look at this dh over dz. If we look at the h, if we didn't have the z component, then the h over dz would be 0, then we don't get any momentum. That's why we need that there is a z component in it in order to accelerate the atoms upwards, up, how to say, in positive z, right? So this Stern-Gala, wherever they knew this, because they didn't know anything about the dynamics, they had a feeling for it. They need a inhomogeneous field. That's why they put it there, because if you have an inhomogeneous field, then you get a momentum thing. So P, after time delta t, or small dt, it doesn't matter, goes to P plus dp. Okay, and this is exactly what happens, right? So this is the quantum mechanical way of writing things. Of course, we can even write it in this form if we go to the Heisenberg picture, which I don't want to use now. But in the Schrödinger picture, where the states carry the time dependence, it's really like this, that we can say, if you have a z in the potential, then you will move this is like a force. You know, if I have a potential that depends on z, then this will make a force in z direction. Because the potential, if you want to get the force, you have to take the derivative of the potential, negative derivative of the potential to get the force, right? And that's why this P will change in this direction, okay? So basically now I can use this because there is a thing that says that that if this is true, if this equation holds, then also the following equation is true. Namely, if I take P and I act from the right with this operator, minus I, let me see, delta P, minus I delta P, and then Z, then I get, and I must here must put a plus, because everything that is here on this side, if I turn it into brass, if I turn it into a functional, then I need to take the complex conjugate. This is because of the inner product. It is like this. Just believe me. So this becomes P plus dP. Okay. So this is the case, and now I know what is happening. Then I can put here P plus dP. Sorry, here I can put a P plus dP, and here I can put, because with the plus it goes like this, and with the minus it goes like this, and then I can put here minus P. And that corresponds exactly to the two wave functions. So this was just high calculation again. Now let me put the whole thing over there. Do you have questions concerning this? No? Yeah. We have to make a break in a second. I just wanted to finish this because I don't want to spend the whole afternoon on this, but could, of course. Could, of course, do this.
And then we can go to the surface where we don't need physics anymore and everything becomes very simple. So here we have now let me repeat this. So I have P and then E up to the plus minus I over H bar mu B, let's just call this delta P, delta P, and then Z, okay, and here is psi 0. This is nothing else than P0 plus minus delta P psi 0. And this is nothing else than the wave function. And now at a different point, then we P plus minus delta P. All right, psi 0. Wave function, the momentum representation. And this means I can now write my psi, capital psi of delta T in this way. So capital psi of delta T. The last sort here. We know now what to do with this part. And I just want to write it as okay, so we have here integral d3p, and then d3p. Then we have C0, e up to the minus I, H bar, mu p, E0, delta T, and then comes the psi 0 of P plus delta P, and then P, and here is 0, and then where am I? And then comes a plus here, plus C1, e up to the I over H bar, mu B, B0, delta T, and then psi 0 of P minus delta P, and then P 1. And this whole thing, I can now write, now it becomes simpler, I can now write a C0 psi up 0 plus C1 psi down 1, where the integral d3p of psi 0 with the p behind is this thing, and the whole integral with the wave function with minus delta p is this thing. And I call them like that because this one is the one that moves up, where the center of mass moves up, and this one is where the center of mass moves up. All right. So can you see that, or shall I write it? I can write here. Psi up and down is equal to e up to the minus plus I over H bar mu B B0 delta T integral d3p psi 0 of P plus minus delta P P. Okay, so this is just a definition of these two things. If the up, the function of the dot. So, and now comes the thing. Now I'm actually there where I wanted to be, and I really apologize for the long thing, but it is really a little bit involved. Once you have that, you can actually look at it. And now you can see that it could be that these two wave functions, that these two that these two states of the center of mass are orthogonal. Okay,
If they are orthogonal, then everything is fine. Then I just have to look where did I measure them? Where do I measure them? I will do the measurement, the actual measurement process in a moment. I will then find it in the upper half if it's 0, and in the lower half if it's 1. But imagine they are not orthogonal. They overlap. You don't separate them. The two wave functions don't go far enough. Then they are overlapping. And then we have non-orthogonal so-called pointer states. And this is not a projection measurement. This is an unsharp measurement. This is something very important in quantum mechanics because it happens most of the time. We don't have these ideal projection measurements. No, we have these measurements that we call unsharp measurements. And then things are different. And that is basically what I wanted to teach you in this hour. So after this phase where they coupled, I coupled the spin to the center of mass motion. I find that the center of mass is now moving upwards if it comes with the spin up, and it's moving downwards with spin down. That basically separates the two things. And then I can measure them. See, this is the trick of measurement. And now we have to do the actual measurement, which means we have to see where on the screen are they, right? And I'm gonna do this. I'm gonna do this hopefully in a simplified version over there. So what happens now is the following. This is, by the way, the last one was 3, and this is 4. Okay, so this first process where we had psi of 0 going into C0 psi up, 0 C1 psi down, 1. This is called the pre-measurement. So this is the pre-measurement. This is the phase where you couple your observable, which is the sigma z, to some pointer observable, where the pointer here is just the center of mass motion of the thing. That's, the idea of a pointer is in the measurement. You have a measurement apparatus and always a pointer, right? And depending on what you want to measure, you find the pointer here, or you find it here. And in this case, it's the atom that is the pointer. It flies up and makes a point here on the screen, or it flies down, makes a point here. That's the point. Okay. So the pre-measurement is always coupling of the observable. This is the observable of the system. The one of the system. To an observable of the pointer system. We call it just a pointer. And the pointer here is just the center of mass motion, center of mass of atoms. Okay, that's the point. Right, so that's the pre-measurement. And now comes the second phase. In the measurement, there's always 2 phases. The second phase is the projection phase, or sometimes we call it the objectification phase. Sorry for this complicated word. So objectification So the objectification phase in our case is the atoms. The atoms hit the screen, hit the glass plate, and make an indent. Make a trace, make an indent. I just call it indent, like a small dent. Okay, make an impact. each, you know? Right, the dynamics of the thing are not clear. Why are they not clear? I mean, if an atom hits a glass plate, why is that not clear? Well, you must imagine if I'm in a superposition, then what happens now suddenly is that the atom only leaves a trace in one of them. I mean, even though it has two components, somehow it leaves a trace here with probability 3/4 in our case, or with probability 1/4 downstairs, right? And why in this one, at this particular point, and not in this one? You know, how this happens, this objectification of the value of the observable is not clear. No one knows. It's the measurement problem. We discussed it for 100 years. We don't know what it is. We don't know what it is. Some of us, I'm one of them, we believe that this is a natural thing. So what happens here is you have the atom moving on both things, not really moving on both things, but the possibilities evolve that the atom can leave a trace on the upper part of the glass plate and on the lower. And in the measurement itself, there is some how can I say, some it's becoming real, no? So from possible to realization of one of the possibilities. And it must happen that it hits only on one. I mean, that it leaves the trace on your one and not on both. But even if I believe that, I cannot really say how the dynamics of it. No, I don't know at what point this happens. Is it just a point in time? Or is it over a time point, over a time period? I don't know. I don't know. And I think no one knows. But this is the special thing about quantum mechanics. And now what we do is we just calculate the probability that we make an indent. Okay. And this probability is like always given as the expectation value with respect to the state before of a projector, and the projector is the projector onto a certain position eigenstate or onto a certain area of that is spanned by position eigenstates. So usually, you know, the hit is not in one point, it's in an area. We'll find it in an area. So this px here looks like this. It's an integral over an area. Okay, so this is what it is. And yeah, this is the px, and we can now calculate the same. And if we do that, then we'll find two components. Okay, maybe let me clean this. Let me photograph this and clean it, because it gets too far down. Okay. Yes. All right. Well, I stopped here, so yeah, I should actually, before I do this, I should on this side. Okay, good. So I just wrote something here, but this is a nice question. But thank you. Leave this on the ground there so that I can build on it. All right, so. So I wrote down the probability, but I have to also write down what happens to the wave function. Okay, so which is a little bit of a thing because it's not totally clear whether you find your atoms back after they hit the screen. But let's say there would have been small holes, then the following would happen. So it would go to psi x, okay, where this is integrated over some x, over some area x, okay. So this is small area, you know, it's like this is small area x, right? So over the small area x, so there is some x, some area on which it lands, and this psi x is given by 1 over the probability that you find this thing, which is down there, and then px onto psi of delta t. And we must be a little bit careful because, you know, the question is, do we have here this thing or do we have here that thing? And for the moment, I want to make it general. I want to just look at the position, the set of mass part. All right, and no, in fact not. In fact not. I will take the full thing, so psi of x, and then I have to still put my things here behind. All right. So this px only goes not on the center of mass, but I mean it goes only on the center of mass part, but there is the spin part still in there, and we will now see how this really acts. So psi of x is equal to 1 over square root p of x. Then we have integral d2x x, and then there is x, and then there is c0 psi up, psi up of x and 0, and then plus c1 psi 1 of x, and then down, and then 1. Okay, so this is basically what I got from somewhere. Yeah, somewhere that I have now deleted, but some part where I had defined the up and down states, and this state is just you know, this wave function is just the projection of the state onto the position vector, but in a two-dimensional plane. So x psi up. Okay, and this thing here is x psi down. All right, so this is okay. So now I have done this, and I'll write it a little bit differently. Namely, I take this. If I integrate over this, I get some vector that points to the middle of this thing, and I will take this out, and then I have is equal to 1 over square root p of x, and then there is a x, and then there is a c0 u up x 0 plus a c1 u down of U down of 1. Okay, where I have assumed that over the small point, the wave function doesn't change much. So over the small area, okay, the wave function is constant. So psi up of x is equal to constant, and psi down of x is equal to constant on this area x, on area x. Okay, usually this area is very small, and I can assume that the wave functions are constant, and then I get here the following form, namely that u so u1 or u up. I don't need x actually. Do I need x? No, I don't need an x. If this is true, then I don't have to put an x there, and then I can write the u1 as, where do I have it now? The u1 is given by, where do we have it? U1 is just, if I see it correctly, is just psi up of x, which is constant. Okay, this is just this. This was u1 or u up, sorry, and this was u down. And for x out of x, and so this is actually clear. I don't have to write that x especially. So this is psi up of x, and this is psi down of x. This is fine, and then I just have to explain what the x here is. The x is 1 over the norm, so we have to normalize this thing. Dx integral dx x, and NCM is integral d2x over x, right? And then I have to actually put this. This was not true. I have to put this as divided by let me see, divided by NCM, because then this together with this gives the right thing. Okay, NCM here divided by NCM. So it's just some normalization constant that comes in there, and then I get this form. So what is important about this form is that now I can totally leave away the description in terms of the center of mass. I can just talk about the spin, okay? And I will formulate everything in terms of the spin, and we will see that that depending on these coefficients, we recover the ideal measurement from before, or we get the unsharp, and it captures both. So that's basically the last thing that I want to write down. Okay, so now I write the whole thing much easier. So I come back to the easy part. Let's see, this is 5. Okay, but before I go further, I have to ask, are there any questions? And what is the time? Was this took longer, much longer than I thought it would? But what can we do? So the thing here is on constant. For x things, size 0, yeah, this is still in the side. Okay, so do you have questions? And what time is it? Here. 3 foot. Good, okay, right. Okay, 343. Okay. Good. Then, we have two possibilities. Either we go here a little bit further, because now I'm basically back to the description without the center of mass, right? Where I can teach you a little bit about the way how one describes measurement in the modern formalism. You don't need to do this necessarily, except you are kind of building these machines, right? And now you know how to do it differently. Oh, it's a calculation first, and I know that it's a lot, but I think it's worthwhile that we went through it. You have to see it once in your life, okay? And I would suggest that I bring it to the end, because then we have it, and we have the new description. The other possibility is that I switch to the communication part, show you a few slides there so that you know something about it. That's the other possibility. But I can think of a third possibility, namely the possibility that I now finish this, and I can imagine that there is still some time at some point in the next 2 days where I can show you some slides in between. The slide is not so much a problem. I can even send it around, although it's better if I explain. But you decide what we should do. I think, in order for this to make sense, I personally think the best thing would be to show you this description. The easy description that you get from this is much more general. Would that be okay? Yes, okay. Let's do it. So now comes hopefully the easy part. Should I take away this part and then write there, or should I write down here? Better up, sir. Okay, and we don't need this. So we've done it once. We don't need it. So now we come to this point 2.1. I think there is somewhere 3 description without the center of mass. Without the center of mass. Okay, let's take another pen. So in that case, I write a probability, and I have to write the state after the measurement in this way. So I take the probability to measure it on some area that's small. So where the array function is constant, that's important. So x is small enough, and then I can just write here an operator e of x with respect to the state phi 0. You remember the state phi 0 was just the state of the spin system, right? So how does that work? Well, this works like this. We have P0. Sorry. I have to first write the EX. So EX is P0, P0, and then 0, 0, plus P1, 1, 1. Okay, where these P0s and P1, we had it at some point, I think, on the board. It's basically just the modulus squared of these things. Okay, so modulus squared of this and modulus squared of that is P0 and P1 respectively. So if I set it up like this, then I get for the probability the right thing, because the probability is then just equal to the probability is equal to P0 times C0 squared plus P1 times C1 squared. Okay, and we know that P0 is equal to U1 squared, U0 squared, no, U up squared, sorry. And P1 is equal to U1, U down squared, so U down squared. All right. And so I have an expression for how to express that probability. And what's the difference to what we had before? You know, in the beginning, we had this projection measurement, right? And what was the probability? How did we calculate the probability to get spin out? How did we do this? Do you remember that? So we actually have just the expectation value of this projector, while this thing here is now a convex combination, or it's a linear combination of projectors. Okay, there's still a positive operator, you know, so it means that the eigenvalues are positive and the expectation value is positive, so that I get a probability, right? But it is not anymore a projector. So that's more general than a projector, right? And for the wave function, I must do the same thing. So the wave function was in the beginning phi 0, and if I measure x, then I get 1 over square root p of x. This was, you know, this 1 over p of x that we had here. But this should have not been, this should have been x like with this area x. So 1 over square root p of x. And then we get C0 u up 0. Let me make an x here just to remind us that, you know, we had the measurement result x, and this value, of course, changes depending on the measurement result, plus C1, and then u down x1. Right? And in other words, I can call this now phi x. So phi 0 goes to phi x, and phi x can be written as an operator acting on phi 0. Okay, where I have to be a little bit careful, because in principle, I would like to exclude this normalization from this operator. Otherwise, you know, with the normalization, it becomes a nonlinear process. So I will put this in brackets and then call this thing here. This is right. Just see. I call this thing here phi 0. Yes.
phi 0. And then I say that M acting on phi 0 gives phi x. And what is this M now? M is nothing else than U1, U up x 0, 0 plus U down x 1, 1. Okay. And what is the, let me put an x here. What is the relation to the EX? Can someone see that? So how do I get from the MX to EX? Can anyone see that? What do I have to do to the MX to get the EX, where I know that the P0 is given by this? The idea? Well, I have to, if I take MX adjoint times MX, then I get EX. So adjoint means just that I swap the things around, but 0, 0 gives 0, 0, 1, 1 gives 1, 1, and I take a complex conjugate of these. Then if I multiply the complex conjugate, I mean the same thing with complex conjugate coefficients here, then I just get this form P0, 0 plus P1, 1. All right? Yes. Okay. So this is the trick, and basically what now happens is that because of the probability conservation, so I must have some P of x is equal to 1. So if I sum over all possible x's, for all possible areas that I can get, if I sum over all of them, then I must get 1. And that means that two things, namely that the sum over the ex's over x must be the identity. And on the other end, also because of this identity, the sum over these measurement operators must also be the identity. So let me give you some notions. So this EX is known as effect of the measurement, and MX is called measurement operator, or sometimes Krauss operator, because Karl Krauss was someone who wrote a book about these kind of operators, measurement operator or Krauss operator. Karl Krauss wrote this book in the beginning of the 80s, but he wasn't the one who invented it. It was already invented by his teacher, Günther Ludwig, in the 70s, these Krauss operators. And now we can describe any measurement in terms of effects and measurement operators. And the only property that we need is that the effects sum up to identity. Otherwise, we don't have this probability conservation. And that the MXs fulfill the same property. So MX adjoint. Okay, so if you take the adjoint of the operator, this just means, if you take the matrix, you split at the diagonal and put a conjugate of all matrix. Then you have any such collection of Krauss operators,
mx. So we often write it just like this, mxx, or we write ex x. So any such set of cross operators can in fact be realized by making an indirect measurement. So by making exactly what we had before, so we take some system, we couple it to a pointer state, and afterwards we make this projection onto one of the pointer states, okay, eigenstates of the pointer observable, and then we have realized such a measurement. So any generalized measurements, these are also known as generalized measurements, can be realized in pretty much the same style as we've seen it for the Stern-Gerlach apparatus. Right? So this is what can be done, and we went now two ways. The first way was just to look. We first looked at the general description, at the abstract description of spin measurements, of spin half systems. Then we looked at the realization of that measurement, which was quite complicated. And from that, we found a way to actually leave away the pointer states and which was the center of mass of the silver atoms, and find a very general description that is valid for all measurements that we know. Okay, these are called generalized measurements. Okay, I think I'll stop here and ask you first for questions. And then I hope that you might find a little bit more time later, tomorrow maybe, and I can show you some slides about the field protection, right? But I think it was a necessary exercise that we went through, and I really thank you for your patience, because it was a long process. All right. Can I have any questions if there are any? I have my feelings on it was too much. Yeah, sometimes it's a lot. All right. Questions? Okay, so then let's not exaggerate this. I thank you very much for your patience, and I hope to see you maybe tomorrow. But I for sure see you around. Okay, so all the best, and thank you for the nice questions in between, and all the joy that I had to teach you. Thank you. 10 minutes break. Then I think, sorry? I think I started, when did we start? 10:15? 2:30. Yeah, really? We start only at 2:30? All right.
Stay eyes. You already not yet decays to brownstone. Mike? Somebody has the mic, but the mic is going now. Okay, even better. No microphone. Okay, good. So we work without microphone. Should we? Okay.
Today, professor, we just finished.
Thomas took the microphone with him. That's fine.
Okay, maybe let me start on this, right? Because time is flowing. Okay, so where did we, am I loud enough for the people in the back? Do you hear me? Good. If you don't hear me anymore, you complain, please, okay? In a way that I hear you complaining. Yeah? Good. Okay, so we finished, right, with the James Cummings Hamiltonian. James Cummings Hamiltonian in the, which was also the rotating wave approximation, right, of our light matrix connection, right, of the coupling between the two-level atom and the field. Okay, so we have so we have started with that, and what? So what was the basic structure of this? So maybe even now with at resonance, so delta equals omega minus omega, which was the detuning between the frequency, the eigenfrequency of the unperturbed atom, right? So the level space between the excited state and the ground state. And capital omega was the frequency of the harmonic oscillator, which represents the monochromatic driving field, right? Now we said this, we say we are really at resonance, so this difference is zero. So then how did the Hamiltonian look like? Or how does this James Cummings Hamiltonian look like? What's the structure? Any suggestions? So remember this exchange of excitations between Yakubu and me. So you need one agent which, I mean, de-excites the photon field, right, and excites the atom, and the other agent which de-excites the atom and excites the photon field, right? Therefore, it was A sigma dagger plus A dagger sigma. Right? And in the presence for delta different from zero, then we would be H bar G, and then A sigma dagger, and then it depends a bit on the convention, which I never remember myself. So this is exponential of minus I omega minus omega T plus A dagger sigma exponential of plus I omega minus omega times T. Right, this parenthesis is closed. You have to take photos of them, they are much more important. Okay, right, now we want to find solutions of this of the Hamiltonian of the Schrödinger equation generated by this Hamiltonian, right? So now we make an ansatz for the wave of the state of the atom and of the field of state of atom and field. Now remember, right, we describe a system which has one degree of freedom, which is the atomic degree of freedom, and one degree of freedom, which is the field degree of freedom. So therefore, when we describe now the state of the complete physical system, it's a state of the atom and of the field. And that's, let's say, in the jargon of quantum optics, this is also what we call rest state of the atom. Yeah. So the idea is, or the imagination is that the atom is stressed by the photon. Okay, so that's so therefore, in some sense, what we do here in its elementary form is what is called rest state theory of light matter interaction, right? And so we make an ansatz for that, And so we write psi of t in the interaction picture is given by a coefficient, an expansion coefficient n e, which will depend on time under the time evolution, right? Times the photon field in the state, in the Fock state, in the energy eigenstate n. So it's like this. And the atom in the excited state, plus Cn plus 1 g of t as the amplitude of the state n plus 1 tensor g, right? And the short form of that, I mean, in principle, I mean, I say the correct, mathematically correct way is to spell out the structure of these eigenstates or the structure of the underlying Hilbert spaces, right? Which is the Hilbert space of the photon field and the Hilbert space of the atom. So, which are, I mean, which are two factors of the tensor space, which is given by the tensor product of these two Hilbert spaces. But then the short form, the short notation for this state was then n e, right? And this is n plus 1 g. Okay, now why is this ansatz general enough for a state of the total system? So why don't I take other values of n? I mean, let's say here you see I only have n and n plus 1, but there's no n plus 2, there's no n minus 1. Why is this sufficient? Right? Because I think you mean the right thing, right? Because it's only these states which are covered by the Hamiltonian, right? So as we saw before, throwing this bottle, right? So if you are in NE, right, you come to no other state but in n plus 1g. If you are in n plus 1g, you come to no other state NE, right? So this is a special property of the James Cummings model, right? But in the James Cummings model, you're always Okay, so maybe then I start again. Let's say next one is the important part. So okay, for those who just came now, right? So what I did, I recapitulated which is our interaction Hamiltonian, right? In the rotating wave approximation, where I dropped what? I dropped the rapidly oscillating terms, right? Also the energy non-conserving terms in different ways of describing them in the jargon, right? Then I have just this h bar g. G is the coupling strength, the coupling constant. And then I have this a sigma dagger plus a dagger sigma, and if I have still a finite detuning delta, which is just the difference between the two frequencies of the field and of the atom, then the coupling Hamiltonian has this, or the James Cummings Hamiltonian has this form. And then I said, and now I will write down, I want to find the solution, right? Or I want to find the solution of the Schrödinger equation in the interaction picture as generated by this Hamiltonian, right? And then I make an ansatz for the state of the atom and of the field, which is also known, these joint states of atom and field under resonant coupling. They are also known as stress states of the atom. Okay, the atomic state is stressed by the photons, right? So that's the idea is that the atom is in some sense surrounded by a cloud of photons, right? That's why people call it stress states. It's originally done by, I mean, I mentioned already Serge Roche. So Serge Roche came up with this theory. So therefore, the original. Is there anybody who is francophone here? Anybody who has actually speaks better French than English? Ah, okay. Yeah. So this is also known as état ami So the stress states are also known as the Gravier. Yeah. Okay, and so then I was making this general ansatz, and the question was just when you came in, right? The question was why it's enough, why it's sufficient to have only expand the general state only in the state NE and state n+1g, and this is due to the fact that James-Cummings Hamiltonian does only couple. n+1g is only coupled to NE, and NE is only coupled to n+1. It's in a sense an on-shell description, as you would say in nuclear physics, an on-shell description of this. Okay, and now what we do now, we go now with this into the Schrödinger equation. Into the Schrödinger equation of the in the interaction picture. Okay, remember, right? So we had the Schrödinger equation, which was in the interaction picture was IH bar dt psi I equals VI psi I. Right now I use for the VI, I use this, right? And now I just apply that, right? So so I get psi dot. And then I also see, wait, so what do I also see? I see that here's H bar, right? Here's the H bar, so this goes away, right? And so I adjust this one I hanging around somewhere. So now psi dot. So the time derivative of psi, right? Is now by virtue of this expression here of this ansatz, it's CNE dot times NE plus Cn plus 1 G dot times n plus 1 G. And this now, if I take the right hand side of the Schrödinger equation, right, I get minus I, and the minus I comes from dividing through this I on the left hand side, right? Dividing the entire equation by I. So I get minus I, and then I get, now I take the explicit form of the interaction Hamiltonian, of the James-Cummings Hamiltonian, K sigma dagger plus A dagger sigma. Yeah, and this now acting upon C and E plus C n plus 1 G n plus 1 G, which was my original ansatz, right? And okay, so now what I get. And now what I want, actually I want, you see now, this is in principle, I did now an ansatz in terms of the time dependence of the amplitude of the basis states. The basis states are NE and n plus 1 G, right? And now I want to isolate essentially this this CNE dot, because then I get the differential equation for a CNE dot or for CNE, right? And this I can integrate on you, right? And so how do I isolate now this object, the CNE dot, in this equation? What do I have to do? So when I want to get an expression for CNE dot, what do I have to do here? So questions? No? So look, these are all states in a Hilbert space, right? Vectors, right? So now, and they are orthogonal, right? So what I can do to get only this term here, this scalar, right? I can multiply the equation from the left, right? If I now multiply the equation from the left with n comma e, and I do this with the entire equation, right? Then you see that I get, I get the psi dot on NE, right? And this then is essentially given by CNE dot, right? Because this here gives me 0, right? And so then the right hand side will give me the non-trivial part of this equation. If I do that,
I get C N E dot, right? This becomes, I mean, N times NE on this gives 1, NE on this gives 0, right? So this falls away, vanishes, right? And now I go from the left on this expression here, where A sigma dagger acts upon NE, right? So now I see that A sigma dagger on NE, what does this give me? What does this give me? NE, A sigma dagger on NE. The action of A sigma dagger upon NE. Right. Sigma dagger upon NE. How many states do we have in the atom? 2, right? And the upper state is E, right? So if you want to excite further on, I mean beyond E, there is nothing to be excited, right? So therefore, this actually gives 0. Sigma dagger on E gives 0, right? And this is actually, when you look back in our first lecture, right, we defined, I mean, the vector representation of E and G, and we also defined sigma dagger and sigma dagger was something like, right, a matrix like 0 in the first row, 0, 0, 1, in the second row, 0, 0, right? And sigma was something like in the first row, 0, 0, in the second row, 1, 0, or vice versa. I always mixed up, I always have to check it myself, right? But it was of this structure, right? And then if you apply now sigma dagger on the vector which was representing E, you will see that it gives 0. Actually, it gives the vector 0, 0, which means the neutral element in the vector space. Okay. Okay, so this term doesn't give us anything, right? Now this on this, what does it give us? A sigma dagger on n plus 1 G gives A sigma dagger on n plus 1 G gives A sigma dagger on this. Suggestions? Suggestions, opinions? A sigma dagger on n plus 1. This can also be written like A n plus 1 tensor sigma dagger G, right? If I decompose the or make the tensor product structure explicit. Now A upon n plus 1, which gives what? I want your real voices, please. On top, there's this background noise, right? So now you see, it's again like a quantum computer, right? There's background noise. So you have to be either louder or faster. Okay? So A on n plus 1, this we had this morning already. So square of n plus 1 times n. Okay. So and then sigma dagger on G, you just simply E. Okay, just excites here. Okay, clear? So therefore, and then now A dagger sigma on NE gives what? A dagger sigma on NE. A dagger sigma on NE. A dagger on N gives square root of n plus 1 times n plus 1, right? And sigma on E gives G. Got it. Okay, so and A dagger sigma on n plus 1 G. A dagger sigma on what does sigma with G? Sigma with G. You are on the ground state, you want to de-excite further, can you? 0, right? So therefore, I mean, from the application of this of either this one or this one on the state on the right, right? We always get a non-vanishing contribution only from one of these two terms, right? Yeah, and so now I write it down. So I get, yeah, now I'm interested. I mean, since I project on NE, right, I'm interested on that term which is produced by the application of this operator on this state, which is proportional to NE, right? And the term which is proportional to NE is this one, right? Because let's say by acting with A sigma dagger on this one, I get NE, right? With the prefactors Cn plus 1G and the prefactor square of n plus 1. So I get sigma, Cne dot equals minus I, right? Minus I, and then G, right? Wait, did I miss G there? I left out. Yeah, there's a G missing here. Here, look, I forgot the G here. Here's the G missing. I forgot that from this here, right? So I get minus IG times square root of n plus 1, which comes from the action of, in this case, A dagger on, in this case of A on n plus 1. Yeah. And then Cn plus 1 G, right? Because this on this gives me Ne multiplied from the left. With the blah, and E gives 1, and so the only thing which is left is this one, right? So I get this, and the same accordingly, if I multiply now this equation from the left to n plus 1g, right? I extract this time derivative, and so I get n plus 1g gives me Cn n plus 1. G dot equals minus I G square root of n plus 1 C n E. Right, and these are now my equations of motion for the amplitudes. For the amplitudes of a general rest state of the atom in the field, right? Don't neglect these. Yeah, I stand up to see it, right? Come forward, right? So I read it to you again. Okay, so I make this ansatz. I plug this ansatz into the Schrödinger equation in the interaction picture. I project out the component Ne and the component n plus 1g by multiplying from the left or with the bra vectors Ne or n plus 1g respectively, such as to extract the derivative, the time derivative of the amplitude of the state Ne, or the time derivative of the amplitude of the state n plus 1g, right? And this, so to say, I mean, inferring the dynamics from the dynamics of the expansion coefficients, right? It's also called the amplitude formalism. So essentially, we solve the problem now in the amplitude formalism because we solve the equations of motion for the amplitudes, right? And now, if you now solve that, you get the following result. Great. And for, and I don't do the solution, I just give you the result. I'm sorry. So I don't do the solution, I just give you the result now. So, so you get then at for the initial condition for initial condition that C and E at time equals 0 be 1. Right, so this means at the beginning you have n photons in the mode, and the atom is in the excited state, right? And accordingly, for because of normalization already, n C n G at time equals 0 is 0. Yeah. Get C and E of t equal cosine of G times square root of n plus 1 t, and C n plus 1 G of t equal minus I sine of G square root n plus 1 t. Okay, so this you can, let's say, if you do an exponential ansatz, essentially you see this quickly, or you can just verify that these solutions, that these are really the solutions of the equation. And now, let's look what this means, right? So these are now formally the solutions. So we know now how this state evolves in time, how essentially the population and the amplitudes of this component and this component evolve in time, right? And now we look at what this means in terms of certain observables, which we could measure on the atom or on the field, right? And so what we do now, we calculate now first the probability to find the atom in the excited state, right? So we take psi of t and we project it on E, right? And we take the modulus squared to say what's the probability to find the atom in the excited state. And so this is P, was written as P sub E of t. And this then is nothing else but cosine squared of G times square root of n plus 1 times t. Yeah, and correspondingly, the ground state, psi t G, modulus squared is probability to find the atom in the ground state is a function of t, then sine squared of d square root of n plus 1 t. Okay, let's see that, right? And now, further, we can, for example, ask, okay, so what's the probability, what's the expectation value of the amplitude of the field? So now I write this here. This is now the amplitude of the field. Amplitude of the electromagnetic field. Yeah. So this is psi of t in the interaction picture. So the diagonal element or the expectation value of this field operator, or the operator which represents the amplitude of the electromagnetic field. And this is nothing else. We had already used it up above. Psi of t, right? Then A dagger plus A psi of t I. And this now, if you do a little bit of calculation, if you just, I mean, you follow the rules which we have, right? So you know how A dagger acts upon
the component n or n plus 1 of the state, right? Likewise, we know this for A. And then for the rest, you just evaluate color product, right? And then actually you find that this is 0, right? This is a bit surprising. And this, the reason for that is that the state reason field in energy eigenstates. Right? So but that's now just an observation, which I will not further comment upon. But then I can ask, okay, how many photons are in the field, right? So how many of these photons, which we were exchanging at the end of the last hour today, right? How many photons are in the field? So then I would write the expectation value of n, the number of photons in the field, right? Would be I psi of t a dagger a, which is the number of photons, right? A dagger a counts the number of photons. Psi of t I. There you find then, if you do the calculation, you find n plus sine squared g times square root of n plus 1 t. And we see now that in the field degree of freedom, right, as a function of time, you oscillate essentially between, since this is just a function which is strictly positive, it's bounded by 0 and 1, right? So the number of photons in the field oscillates with a frequency given by g times square root of n plus 1 between n and n plus 1. Okay, yeah, you see that? And then final thing, right? We still calculate the variance of n. Variance of n, variance and time. So the variance of n and yeah, which is defined as n squared, the expectation of n squared minus the expectation of n squared, right? This then, okay, so you write n squared, I mean bracketed between psi of t, right? The same with n, right? And you will evaluate that, and then you find this gives 1/4 of sine squared times now 2g squared of n plus 1 t. Okay? These calculations you can easily do yourself, it's not difficult, right? So, and what I'm now going to do, after you copy that, I will take these formulae away and then we'll replace them by pictures, right? So we see a little bit, we get the more imagination what we are confronted with. Maybe one remark already now here. So you see that now here the probability to be in an excited state oscillates simply with frequency g 2g n plus 1 square of n plus 1, right? And likewise for the probability to the ground state, right? And so if you imagine now the Bloch sphere, right? At the beginning, I asked you whether you're already familiar with the Bloch sphere and what the Hadamard gate does. The Hadamard gate wants to get you from either one of the poles into the equator of the Bloch sphere, right? And so now here, because of this continuous evolution of the excited state population and of the ground state population, can imagine that somewhere in between, for some time in between, right, you will just have a coherent position between the excited state and ground state, like a balanced coherent position. So you will be on the equator, right? So this means that this dynamics here already allows us, if we were now to make the atom interact with the light field for a time, for a specific time, right? We can anticipate that this will allow us actually, this dynamics actually realizes the Hadamard gate for a specific illusion. Right. And now when would you expect that? I mean, when would you expect that you are in this balanced position, given now these expressions that you have here? And please look at these expressions in this line, and look at this expression here, right? At the variance, right? You see the variance is oscillating with twice the frequency than all the other expressions, right? And it's also oscillating, okay, between positive maximum and minimum values. And when would you expect to have a coherent superposition, a balanced coherent superposition, or to be in the equatorial plane of the loss here, when you have maximum variance or minimum variance? We'll see this in a few minutes in the pictures, but now what would you expect? So look, when I have this here, when the population of the excited state is 1, right? Then also this here is by at least its modulus is maximum, right? So it's 50 to 1, right? So this means essentially I need to have that g times curl of n plus 1 times t has to be integer multiples of pi. Sorry, yeah, right. Because cosine 0 is 1, cosine pi is -1, cosine 2 pi is 1, cosine 3 pi is -1, etc. Right? So the square is always 1, right? And so anytime this is 1, at least the modulus, I know that I have, I certainly have the, I'm certainly in the state of the field with n photons, and the atom is in the excited state, right? And whenever this is 1, I am certainly in the state of n plus 1 photons in the field and the atom in the ground state. So when I'm certain to have n photons in the field, which variance of n do I have? And in the sharp. So then the variance is I'm certain that n has a big value. For them, is then the distribution of n values is the financial towards sharp. Okay, so I lost my. But in fact, right, you expect. I mean, whenever you don't know, whenever you have the maximum uncertainty about in which state the field is, whether in n or n plus 1, right? Then of course you have maximum variance, right? Because you can have different values, right? So n squared, n squared, and the expectation of, let's say, it is different, right? While if you know specifically in which n you are, so then just n squared applied on the state gives you n times the state, right? And again, so this will vanish, right? But I will show you a picture. So we expect that we have a balanced superposition between the ground and the excited state just when we have maximum variance. Okay. Now we will convince ourselves of this in pictures. When you took these expressions, when you took photos or whatsoever, yeah, yes, good, prima. So Now I want certain populations of the excited state and the ground state, right? So you need, I mean, you need probably a complete page. So I do it like this. So, well, the x-axis is always the time axis, right? On 3 plots. So the first is I plot the populations. The atomic populations, right? So the probability to find the atom in the excited state or the ground state, right? So, I mean, axis, right? So essentially this indicates the periodicity of these oscillations, which were cosine-like or sine-like. Right? So now it's all I need. Okay, now the population of the excited state will then roughly look like this. See, I'm not very good painter. Right? So this is the PE equals cosine squared of G times square root of n plus 1 times T, right? And then correspondingly, right? So this is essentially then, I mean, let's say any time, I mean, this is essentially integer 10 of pi or pi over 2, right? To vanish of the maximum. And correspondingly, this evolution of PG, right? And since this now goes to cosine squared, right, the frequency with which the populations evolve is actually the frequency 2 times G times square of n plus 1, right? So you actually call this has, I mean, this frequency has a name, right? So oscillation with frequency 2 times G times square root of n plus 1. And this is called omega Rabi. It's known as, come in. So this is known as Rabi. Okay. Click on it. The election is going on. Okay, sorry. So this is called Rabi frequency. And so therefore, these are atomic Rabi oscillations, right? So that's a pretty famous phenomenon in quantum optics, and it's the very essence of doing single gate operations, right? So these are Rabi oscillations. Okay, now we look at and here was the atomic population, right? And now here we plot now the expectation of the photon number of photons in the field. Okay. So now we oscillate between n and n plus 1. This we already know, right? So here is n. Here's n. Say here, so here's 1 here. This was probability 1, probability 0. Right? Here now is n photons, and here expectation value n plus 1. Right? And so now this has the following form. Right? So first we are in the excited state, right? Here, probability to be in the excited state is maximum. So then, since we are only oscillating between NE and n plus 1 G, right? So then this means we have n, we start with n photons, right? And when the excited state population is 0, right, then the photon of the excitation must be as before, right? So when I don't have the bottle must be in the hand of right? So therefore, it looks like this. And now the last thing which we plot is the variance of n. So this now is the variance of n. Right, and this actually oscillates the maximum as we saw from the formula. The maximum is 1/4, right? 1/4. But it was oscillating. We had an expression which was sine squared, I think, was sine squared of 2 times g times square root of n plus 1 t, right? So it's oscillating twice as fast, right? And so the oscillation looks like this. Essentially going like this. Now it's C, so yes, so. Yeah, and the idea is now the plot is certainly, as I'm saying, I'm not a very good painter, but let's say the idea is that this is maximum actually here. Right, so it should be at the same time. Of course, these are supposed to be vertical lines, right? So yeah. Yeah, and this happens now precisely when here you have the probability to find the atom in the excited state is equal to the probability to find it in the ground state, it's 1/2, right? And so here, right, so therefore here actually, at these times, this and this and this, right? You find the state 1 over square root of 2 times n plus 1 g plus n e. Okay, you are just in a weird position of these two states. Okay. So this is essentially, right, then what promotes or what mediates then a Hadamard gate if you wanted to do this in experiment. So the important part is these Rabi oscillations, right? The Rabi oscillations, they, induce a coherent evolution on the blobs here between the ground state and the excited state periodically, right? And if you sort of say wait for the proper time, you are just in the equation. Okay. So now maybe one more remark. Yes, following. So this is not so surprising because if you look now at the eigenstates, if you look at the eigenstates of E, right? G at resonance was GH bar times A sigma dagger plus A dagger sigma, right? now then you can convince yourselves that the state, let's say plus minus, I call these states now plus minus, right? And they be given like 1 over square root of 2 times n comma e plus n plus 1 comma g. Yeah. Then you see that b acting upon plus minus, right? What does it give? It gives, so if you act with a sigma dagger upon this, right? This does give 0, and this gives n e with a prefactor square root of n plus 1, right? So you get g h square root of n plus 1 n e, and plus minus, sorry, the minus here, right? So I take just the even and the odd composition of these two states, right? So plus minus refers to plus minus in here, right? So if I act now with this upon that, I get plus minus times this, and then I act with this on this, because acting with this on this gives me 0, acting with this on that gives me again square root of n plus 1 times h bar g times n plus 1 g, right? So this gives me then plus g times h bar times square root of n plus 1 times n plus 1 g, yeah. And this is nothing else but plus minus g h bar square root of n plus 1 times n e plus minus n plus 1 g. Correct? Correct? Yeah. So therefore you see now that these balanced compositions of these two states are just the eigenstates of this, right? With the eigenvalues, which are essentially, if you wish so, the Rabi frequency, up to a factor 1/2, up to a factor 2. Okay. So this is one important piece of this physics. Yes, let me maybe make one more remark. Okay, so now if you take this as the energy operator, right, and this as the corresponding eigenvalues, right, and now you assume, now I was assuming that the atom was interacting with a field of well-defined amplitude, right? At the very beginning, I put in this interaction term. I said, okay, it's the energy of the atomic dipole in the oscillating field, and I wrote down something like minus E times F, which was the amplitude of the field, times X, right, which was the separation, the distance of the electron from the nucleus, times cosine omega t, right? This then I transformed, without explaining in detail how I did that, into this A plus A dagger times sigma plus sigma dagger times G, right? So in this G, essentially, then I told you at some point, this encodes also the transition matrix element between the ground state and side state with respect to the dipole operator. And so now I can assume now, but now I assume, so G, right, that's also, this is called coupling constant. Coupling constant, or also you can say it's the coupling strength. Yeah. So this now contains all the constants, etc. So it's just all up together under this G, right? But you see that if you have n well-defined, h bar is anyway well-defined, right? And all the rest, it's essentially everything depends on G, how fast these oscillations will go, because this determines part of the Rabi, right? So now let's assume that actually the atom sees a field which has an amplitude which is modulated in space, right? So when do you have this? Let's say, for example, when you have a laser beam, right? A laser beam, you know roughly what is the transverse profile of a laser beam, the intensity profile, how does it look like of an ideal laser beam? typically it's a Gaussian, right? So it's like a Gaussian envelope, right? So now let's assume that G is spatially non-homogeneous, right? So it's not constant in space. Yes. So everybody has these pictures. What? Okay, not confused. Okay. Then you can share the photos, right? So now assume spatial dependence of G. Let's say G of, I don't know, G of X, G of Z. So let's just assume I have essentially here, I have Z, right? And I have G, let's assume now G has this spatial dependence. G of Z. Yeah. So then you see these are the eigenvalues of this operator, of this energy operator, right? So therefore, let's say now if you plot now the eigenvalues, now you plot G of Z times H bar times curl of n plus 1, which is then your running frequency, right? But also the eigenvalue, right? And you see that, I mean, let's say there will be the one with plus and there will be the one with minus. So you essentially will have eigenvalues which go essentially like this and which go like this, right? Okay. So now, if I say these are eigenvalues of the energy operator. Yeah, because this B is here in the interaction picture is my effective energy operator, right? So then what does this mean? Now, what does this mean for the force which is exerted by the light field upon the atom? What does this mean for the force which is exerted by the light field upon the atom? Sounds like a strange question, right? Doesn't it? Yes? Quite clear to you. So, you see, I say this is a Hamiltonian equation, right? Hamiltonian is an energy, right? Now I plug in a spatial dependence of the energy, right? So now, how is the energy or how is the Hamiltonian related? Or the Hamiltonian, so it's an energy landscape, it's a potential landscape, right? Energy is potential, right? So how is the potential landscape related to the force on a particle? How is the potential landscape related to the force on a particle? Who is skiing? I mean, who is skiing here? I mean, I understand there's lots of snow here, but let's say, or who is skiing in sand dunes? What's that? So, or let's say, if you have, yeah. Okay. So when you are up, when you want to climb a hill, right? You have to overcome a force which acts against it. When you want to run down a hill, I mean, before it comes to tension, right? So yeah. And so what determines whether you feel a force which is against you or with you? If you have a potential landscape. What classical mechanics tells you that the force up is the set, right? set was it's a negative gradient of the potential. Yes. So now you see if we interpret the eigenvalues here as the energy eigenvalues, right? So then I get, I mean, let's say depending on in which state you are, in which of the eigenstates you are, right? You see the different eigenstates, the plus and the minus one, right? They see different energy potentials, potential landscapes, right? And so this one, right, it will be repelled from the maximum, from the position where G is maximum, where the field is maximum, right? And this one will be attracted to the point where G is maximum, right? And so this is essentially what you need for optical tweezers, right? When you want to catch atoms with light fields, right? Then you essentially put the spatially dependent by an envelope of by a spatial variation of the light intensity, right? By using a spatial variation of light intensity, you reduce the spatial dependence of the coupling constant, and by this you make the atom see a potential, right? And if you put it in the right state, it will be attracted by those areas where you have maximum intensity, or it will be pushed to the places where you have minimum intensity. So what you often do when people, for example, try to realize a quantum computer, right? They essentially create standing waves, right? So standing waves are again mirrors, right? Again, you need mirrors. So you have a mirror here and a mirror here, right? And then the standing wave is something which fits just an integer multiple of half wavelengths, right? Then here you have the nodal points, nodal nodes. And here you have the maxima, right? Yeah, and if you do this, you can do this in 3 dimensions, so you get a 3-dimensional lattice of light, yeah? And there you can place now, and this is done with Rydberg atoms or so, you can place now, depending on which state you put the atoms, you can place them either at the maxima of the standing light wave or at the minima, right? And they will stay there if there's no noise again, right? Again, there's not much noise, right? That's how you create again now quantum registers made of neutral atoms in light fields, right? And so the basic coupling is again this type of Jaynes-Cummings coupling, which I showed you. So this is all the story which I wanted to tell you now about this Jaynes-Cummings and about this light-matter interaction, which then mediates Hadamard, also is under the background for understanding why atoms can be trapped by light, right? I have done a little bit of, I did a little bit of cheating, right? So I used, but you know, it's, as you say, I mean, good teaching is good cheating, right? But in essence, I can say I wanted to convey a little bit of the idea. So let's see how much time we have. Okay, so I mean, what I could still offer you, I mean, we can either stop now, right? And maybe Henry gives me another slot so I can give a different chapter. Or we could make a 5-minute break and I could give you yet another view on light-matter interaction. But you tell me what you prefer. And it's perfectly fine if you say you're tired, you want to stop it. Right? I have 35 minutes, right? Yeah, but look, let's say, of course, I have 35 minutes, but let's say if I look at you, I'm not sure how tired you are, right? And you see, the cross section decreases exponentially with the flow, right? So therefore, so what do you prefer? 5 minutes break and then we make a short additional story, or okay, so then 5 minutes break. Okay. All set for the last round. Um, very tough. It's a very distant piece. So I thought what I could do now. So now I decided that I present you a little piece of what is known as location DB, right? So that's in some sense it's a generalization of what we had done so far, and in some sense it's a little bit a less general treatment. So it's start badly. Okay, so this we throw away. Next one. So
Okay, so you see, you don't run out of power, but the fans run out of power. Bravo. Okay. So Floquet theory. Again, question: who already has seen the term? Anybody has seen it already? No? 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 Okay, so this actually, I mean, this was a French gentleman, and he wrote actually, he was a mathematician, right? And he wrote a paper on the solution of partial differential equation with periodic boundary conditions. Okay, so that's the original paper, was written in 1881, right? And it's intimately, very closely related to Bloch theory of electrons in lattices. What was the remark? Please repeat. Yeah? What was it? So Bloch theory of electrons, who has heard about Bloch theory in electrons? Who is the solid status here? Or who are the okay, so the solid status? You forgot it? Okay, but the essence is right. You want to write down the eigenstates. So you want to write down the eigenstates of an electron or a particle, right? In a spatially periodic potential, right? So then you have periodic boundary conditions in space, right? And what we will do now, I mean, since we have an oscillating field which interacts with the atomic degree of freedom, right? We take periodic boundary conditions in time, right? And now Floquet theory gives you, in principle, a very general, and a very elegant framework for the solution of atomic matter, if you wish so, under periodic time periodic perturbations. Okay. So general, and elegant framework for matter. Can be in principle, it's not confined to atoms. It will also be, at the moment, this is very fancy, also they run physics, so people try to see, to expose solid state samples to strong periodic light fields, right? And try to see what happens, right? So what typically is often done for atoms, framework for matter under time periodic perturbations. So what you have, essentially, you assume that the total Hamiltonian is explicitly time dependent, right? But no general time dependence, but a periodic time dependence, such that h of t equals h of t plus capital T, yeah, where capital T, I mean, it can be something very, it can be, I mean, this is the only requirement you have, right? So, but I will specify, I will look at the subclass of problems, which is actually precisely the type of problem which we already looked at, only now it's a fully quantized form, which we looked at so far. So in principle, look, it could be, for example, let's say you could have a force like this. So an external force which goes like this, right? Or you could have an external force which goes like a delta sequence of delta peaks. Yeah, and so this would be T.
and this would be T. Yeah, and for all these situations, the theory works, right? I will look again at an oscillating field, which is a cosine oscillating field. So then you have something like okay. So therefore, I will specialize now to the Hamiltonian, which we already had written down at some point. So special is more special case, which, however, is a widely realized case, right? With h of t equals h naught, right? Plus, right? Yeah, fz f times z times cosine omega t. Right, and you see now that this is similar to the Hamiltonian which we already had written down in our previous James Cummings treatment, right? Just that now what we will do, we will not quantize the electromagnetic field. We will really assume that this is just the electromagnetic field is given by an oscillating plane wave, essentially, which has this time dependence with this frequency omega. We have again dipole coupling, so that's again essentially the energy of the electron in this oscillating field. Field has an amplitude f, the position of the electron with respect to the nucleus is z, and the polarization of the field b along the z direction. Okay. I changed a little bit the setting as I did before, but in principle that's the field. And this is the atomic Hamiltonian. So this is just called the matter Hamiltonian. Atom or matter. Right, and you see now that and so this is quantized. Quantized. Now, well, this is a classical fields contribution. To the Hamiltonian, saying this classical fields contribution, I don't write classical field because the classical field would be just f times cosine omega t, right? The fz cosine omega t, that's the interaction between the field and the matter. Right? So when you see that when I write the Hamiltonian like this, right, I treat the field classically, and I treat the target, the matter, the material target in a quantized form. So I take its quantized structure serious, right? So this is also because I treat this quantum mechanically, this classically. You also say this is a semi-classical treatment of the light-matter interaction. Semi-classical, semi comes from, I think, Greek, right? It means something like half, right? So I mean, half the system is described classically, the field, and half the system is described quantum mechanically, the material. So that's why you say it's a semi-classical Hamiltonian in this sense, right? So it's also. And the entire thing is then semi-classical Hamiltonian, semi-classical. Description. Yeah, and now you can imagine that here this field actually is split by a laser, right? Which laser spins the monochromatic field with precise frequency, with a sharp frequency omega, right? The well-defined frequency omega. And so therefore, whether the atom absorbs a photon out of the field or it emits a photon into the field, you assume that this will actually not change the amplitude of the field, right? Because let's say you assume that there are so many photons in the field, right? That adding a couple of photons or absorbing a couple of photons doesn't really change the amplitude, right? And so therefore, you can fix your energy zero. You can fix the zero value of energy of system of atom plus field at the energy content of the field, and so therefore you do not add here anymore what I did above in our earlier treatment. I don't add the energy of the field, right? Because I have the energy of the field is not fixed, right? So I just do all my energy all my energy balancing with respect to the constant energy content of the field. So therefore, I have no additional term here. So this H naught is what was H atom in our fully quantized treatment above. Okay, but let's say these are additional considerations which I don't want to dwell upon too much for reasons of time. What is important now if this is a Hamiltonian, right, that this h of t now is this equals h of t plus t, where now t is 2 pi over omega. Okay? Okay? Yeah. So this is the circular frequency of the field. So then the periodic with this. So we have a case for which locate theory applies, right? And what I will now do, I will now state the statement of what is known as the locate theorem. Once you allow me to take this away. Can I take this away? You just, I wait until you give a green light. Okay? And please, I mean, if I may, please allow me to say that, right? So I think I understand that somehow of the habit, but let's say I'm getting very nervous when you call me sir, right? So you call me together, so it's much, I think, much more. So. Okay. Can I take it away? Okay, so now we say the case. So the case theorem. Okay, I give you maybe I find some notes in English and then I can I know actually these notes are written in English, so I would just scan them and then make them available via this. So given h of t equals h of t plus t, there is a complete set of complete and orthogonal set of basic functions epsilon of t. Now it becomes a bit subtle. Epsilon of t, right? So these are basic functions which also have this, I mean, which inherit the time dependent of the Hamiltonian, right? And that now they are living, assuming that the naked atom, the eigenstates of the naked atom, right? They are living in the usual Hilbert space, which is typically the space of square integrable functions, which is L2, right? So this is square integrable functions. Which span the Hilbert space of H naught, right? So which span the Hilbert space of the unperturbed system, which we expose to this periodic
perturbation. Tensor S1, which is the unit circle. So these are functions. These are functions on the unit circle. So which means which reflects the time periodicity. Yeah, so unit circle is this. I mean, unit circle is essentially this unit circle which reflects the time evolution of this cosine omega t, right? Cosine omega t is living on the unit circle because it just depends on the phase, right? So it has a range between 0 and 2 pi, right? So then there exist basic functions epsilon of t, right, and real associated real values, Epsilon such that e to the minus I epsilon t times epsilon of t times these basic functions. And linear combinations thereof, or superpositions thereof, combinations thereof. And now important, with constant coefficients, C epsilon, it is. So what do I mean by linear combinations of these e to the minus I epsilon t times epsilon t weighted with linear combinations such that psi of t equals c sum over epsilon, c epsilon e to the minus I epsilon t epsilon t is a general solution of the Schrödinger equation I dt psi equals h of t psi. Yeah, where now I put h bar equals to 1. So I set or I measure actions in terms of h bar, in terms of h bar. Okay. And these and the epsilons, so epsilon is called the quasi-energy. Quasi-energy, no problem, right? And the epsilon of t are called the Fouquet states. And now what's important, look, I mean, so what's important is here the constant coefficients. Okay, so because now you see, you know that if we have a time independent Hamiltonian, if we just have H naught, right, which has no time dependence, and we know that once we have a basis of the Hilbert space in which H naught is acting, any solution of the Schrödinger equation generated by such time independent H naught is given essentially in terms of I mean, of expansions of these basis states, right? And now we can here construct any solution of the Schrödinger equation generated by a time periodic Hamiltonian in such a form, right, where we now just have to determine the epsilon of t, the Floquet states and the Floquet eigenvalues, or the quasi-energies, right? And then the C epsilon is just fixed by the initial condition, right? So once I have the initial condition, once I have my Floquet eigenstates and the associated eigenvalues, I can solve the Schrödinger equation for any initial condition, which just fixes the time independent expansion coefficient C epsilon. And now now we have to find out how we find these eigenstates and these eigenvalues. This I'll show you now. So this upper away. Can I take the upper part away? Yes. Thank you. So epsilon of t and epsilon can be found by solution of the following eigenvalue problem of the Floquet eigenvalue problem. Following, which is I minus I dt epsilon of t. Yeah, remember that I put h bar equal to 0, so therefore you know h bar, right? Equals epsilon times epsilon of t. Yeah, and this you can actually see. So this actually comes from if you plug e to the minus I epsilon t times epsilon of t into the original Schrödinger equation, right? So into C, yes. So if you plug this here into the Schrödinger equation, so then you get as well h times e to the minus I epsilon t equals I dt epsilon of t, right? That's the original Schrödinger equation. Times, sorry, e to the minus I epsilon t. I just replaced psi in the Schrödinger equation by this expression, right? So then I get from the right hand side, I get I dt on this gives me minus I squared epsilon, right? So epsilon gives me epsilon. E to the minus I epsilon t, epsilon of t. So that's the same thing which we did this morning, right? Just now again, we take the product rule because we apply this partial or derivative first on this factor and then this factor. Now I applied it on this factor, the second factor. And I still apply it on that factor, so I get plus I e to the minus I epsilon t dt epsilon of t. Yeah, and then on the left hand side I have h e to the minus I epsilon t epsilon of t. Yeah. And so now I just take this part here from the right hand side. This part I take it on the other side of the equation. So I get epsilon times e to the minus I epsilon t times epsilon of t
equals h minus I dt epsilon of t, right? So I get e to the minus I epsilon t, and then h minus I dt epsilon of t. Okay, and now I just can divide by e to the minus I epsilon t, and then I have what I wrote down here. I have h minus I dt epsilon of t is equal to epsilon times epsilon of t. Okay, so this is actually equivalent, right? And so now what you know that there is a time independent Schrödinger equation and a time dependent Schrödinger equation, right? So you see now that here this is essentially h psi equals I dt psi. Right, and now by plugging this in, we transform this time dependent Schrödinger equation into an equation which has the structure of a time independent Schrödinger equation. Yeah, so there is some time dependence, but the structure is that of the time independent Schrödinger equation, because the time independent Schrödinger equation we're used to is something like h naught times phi, say, equals e naught times phi, right? So that's what we're used to, right? And you see now that the operator structure, right, is the same, right? You see that this is now very important to recognize. So if you let's say, so what do we have so far in this lecture, right? In this lecture we had the James Cummings model, right? Then we had the interaction representation, right? And now we have this, right? So you see that in the Floquet eigenvalue equation, despite the fact that it gives the general solution of periodically time-dependent problems, right? It can be solved. It has the structure of a time-independent Schrödinger. So it's actually the structure of a time-independent problem, right? So in some sense, the Floquet picture allows you to represent this problem of a periodic driven system as a time-independent problem, right? Just on a larger space, right? So it has the same structure, but it's living on this L2 tensor S1, right? So in principle, what you get by extending your Hilbert space by an additional product in your tensor product on which you're living, right? You extend you make your Hilbert space larger, but what you get by that, the advantage you get is that you have to deal only with a structurally time-independent Schrödinger equation, right? Therefore, what you find nowadays, often in literature, often people say that actually Floquet, they do a Floquet problem, and by this they look at a time-dependent, by an explicitly time-dependent problem. This is formally a correct statement because, of course, h of t h is actually dependent on time, right? But if you want to understand the true physics, it's actually not correct because let's say, as a matter of fact, the Floquet problems are structure-wise time-independent problems, just living on a larger space. Right? And let me see, what's the time? Okay, it's 6 o'clock. So okay, so I cut it short in a way that I can conclude in few time. So it's short. Yes. That's also okay. I have no space to write it now, but let's say this really have to remember it's a time-independent structural eigenvalue equation. And now what on top you have, right, by this periodicity of the drive, also the solutions actually will be also periodic in time, right? So let me create space. Okay, since you have this structure of a time-independent eigenvalue equation, you can transform this in a matrix representation. The matrix representation with respect to eigenstates on this product space, right? And so actually, further ahead, right? So I don't divide this now in detail. Further ahead, that epsilon of t equals epsilon of t plus t. Yeah, that's, you can also consider this as a statement of the Bloquet theorem itself, right? And therefore, you can extend epsilon of t as a Fourier series, right? So therefore, you can write epsilon of t equals sum over new index k, which is going from minus infinity to plus infinity, so that's the index, e to the minus I k omega t times epsilon k, which are now the Fourier amplitudes of this location. Right? And now you go with this and this into the into Fe, right? This here I call it Fe. So you plug this expression here into the Bloquet eigenvalue equation, and then you get the following. So then you get right. So you get left-hand side of Fe, okay? So H minus I dt, H minus I dt times epsilon, I skip now the axis of time dependence, equals H minus I dt sum e to the minus I k omega t, always h bar equals to 1, right? I k omega t times epsilon k. Yeah. And now you just apply now h minus I dt upon that, right? So you get what do we get? We get e to the minus I k omega t and the sum with parentheses e to the minus I k omega t times h times epsilon k. Right, this comes from multiplying this term inside the sum, right? And then minus the time derivative of this upon the first factor here, right, gives minus I times minus I k omega. So this gives a minus k omega. K omega times e to the minus I k omega t. Like this, epsilon k. So right, and the epsilon k, right? They don't carry any time dependence anymore because they are the amplitudes in the Fourier expansion, right? So I mean, all the time dependence is just now mapped onto these Fourier coefficients here, right? So therefore, I can close the parentheses, right? And this now, on the right-hand side, or let's say now I write h explicitly as h naught plus, or h equals h naught plus cosine plus f z cosine omega t. So now I have all exponentials here, so I write cosine in terms of exponentials. So this is h naught plus 1/2 f z e to the I omega t
plus e to the minus I omega t, right? I rewrite fz cosine omega t, which was the perturbation, time-dependent perturbation. I write it as cosine, I write it as 1/2 times e to the I omega t plus e to the minus I omega t. Okay, and I do this because I have here exponentials, and I want to somehow, I mean, essentially here in this h contains this cosine omega t, and so I want to merge these exponential terms here with these exponential terms here, right? And so therefore then I get sum over e to the minus I k omega t. And now I split h, I split it up into h naught plus this, so I get h naught times epsilon k. And now these two terms, you know, I get two terms, one term 1/2 fz e to the I omega t, and one term 1/2 fz e to the minus I omega t, right? So I get plus fz over 2 times e to the minus. Now I multiply this term e to the I omega t with this term e to the minus I k omega t, right? So I get e to the minus I k minus 1 omega t. If this is plus, right? Then I get e to the minus I k plus 1 omega t if this is minus, right? So therefore I get here the term e to the minus I k minus 1 omega t times epsilon k plus fz halves times e to the minus I k plus 1 omega t epsilon k. Right? And this was now on the left-hand side of the Floquet-Eigenvalue equation. And on the right-hand side, I have epsilon times sum over e to the minus I k omega t epsilon k, right? I get equals epsilon times sum over e to the minus I k omega t epsilon k. Right, and here on the left hand side, I still have to put everything here in brackets. Right. I'm still, you see, I was missing, I forgot this term, sorry. There's one term missing. I'm missing space now. Okay. Still, so we still have this term here. So I have still minus this one, I forgot that one, minus k omega e to the minus I k omega t epsilon k. And this is closed. Okay, so that's now the left-hand side in full glory, right? Photo. Yeah, so the only thing I did, I took the Floquet eigenvalue equation, I took the statement that these are periodic with the same period as the Hamiltonian. I can therefore write them in a Fourier expansion such that the epsilon k are not time dependent anymore, and the time dependence is carried by these exponents by this exponential e to minus I k omega t. I rewrite the cosine in the perturbation, right, in the external field writing in the coupling term as I resolve it in terms of exponentials. I plug that in, and then I get for the left-hand side of the Schrödinger equation, essentially of the time-independent structure like Floquet eigenvalue equation. I get sum over k e to the minus I k omega t h, and then I resolve the h, right, and then I get this here. E to the minus I k omega t h naught epsilon k plus fz halves e to the minus I k minus 1 omega t, same term with e to the minus I k plus 1 omega t minus k omega, which comes from here, right? And then the right hand side, just this, right?
Okay. Now, further down. Yeah, I have to think a moment. Well, I cut it short, I cut it too short, so now I have to think what I how I explain that. Okay, yes, okay. So now I need to see. Now I define to the following definition. Now I do the following definition. Okay, so I define. You see here, actually these terms they decompose into e to the minus I k omega t times e to the I omega t times e epsilon k, and here you have e to the minus I k omega t times e to the minus I omega t times epsilon k, right? So now I define I define epsilon k minus 1. I define as e to the minus I omega t epsilon k. And I define epsilon k plus 1 as e to the plus I omega t epsilon k. And with that, I can write, and with this, I can write the eigenvalue equation as sum over k, right? Okay. And parentheses e to the minus I k omega t times h naught epsilon k plus fz halves e to the minus I k omega t, yeah, right, epsilon. So now I have epsilon k minus 1, right? Minus 1 plus fz halves e to the minus I k omega t epsilon k plus 1, and then minus k omega e to the minus I k omega t epsilon k parentheses closed equals epsilon times sum e to the minus I k omega t epsilon k, which comes from the right hand side. Right? And now I can say, since the e to the minus I k omega t are linearly independent, right? I mean, I can actually drop the sum, and I can, each individual term of the sum has to vanish identically, and so therefore I get that h naught epsilon k plus fz halves epsilon k minus 1, which is this term, right? Plus fz halves times epsilon k plus 1 minus k omega equals epsilon times epsilon k, and this now is true for all k So I actually get a set of equations, right, where k runs from minus infinity to plus infinity. Okay, for all k from minus infinity to plus infinity. Right? And so now therefore in this now we can write as a matrix equation, which is the last thing which I show you. Right. So now if you say that now you define something, we define objects which are similar to the objects which we defined in the James Cummings setting. So this is now my set of eigenvalue equations, or my set of linear equations which I have to solve, right? So now I define A epsilon k equal epsilon k minus 1. And A dagger epsilon k equal epsilon k plus 1. Yeah, and with this definition, I can write this set of equations as H naught plus fz over 2 times A plus A dagger acting upon epsilon k equals, and I put this, sorry, there's an epsilon k missing. Look, I forgot an epsilon k here. Okay. So then I put this on the right hand side. So I get epsilon plus k omega times epsilon k. Yeah, for all k. Yeah, and this now has the following matrix form. Matrix form in a bit of space, right? So now I have on the one hand the matrix in the eigenbasis of H naught, right? And then I also have a basis, another index which is with k, which in some sense labels my basis states. And k is in principle going from minus infinity to plus infinity. So in principle, this matrix is infinite, right? So here I have here I go to k equals minus infinity. And here I go to k equals plus infinity, right? And I get a tridiagonal form of my matrix. How the index be k? So this be say, yeah, okay, so then h, so I can write now h minus I dt, right, which was the original Hamiltonian which I was representing, right, at the following form. So that's essentially this beast here, right? So I have here on the diagonal, in the diagonal blocks, I have h naught minus, for example, 2 omega. So I start with, I just take now some examples, exemplary values, right? H naught minus 2 omega, and I have H naught minus omega, which comes from this structure here, right? So the eigenvalue plus and H naught, yeah, sorry, so H naught minus k omega, right? And then H naught plus omega, or H naught plus 2 omega. Okay, wait. Of the rectangle matrix. This. Okay. And then here I have the fz over 2. Fz over 2 F Z over 2, F Z over 2, F Z over 2, F Z over 2, F Z over 2. Okay, this is now the structure of the Floquet Hamiltonian. This is our Hamiltonian in a matrix representation, right? Which represents on the one hand the k values. So here would be k equal to 2, k equal to 1, k equal to 0, k equal to -1, k. Sorry, -2, -1, right, and so on, right? And so now, if you want to solve the Floquet eigenvalue problem, you have to write down the Hamiltonian in this matrix form, and then you diagonalize this beast, and then you're done, right? Because then you have the epsilon, you have the epsilon k, right? With the epsilon k, the eigenvalues, you get the epsilon t, so that the spaces states which are postulated by the Floquet theorem, right? And then you get general solutions of this of the eigenvalue equation generated by this time periodic Hamiltonian. Right. And so this, I mean, it was a bit fast now. I'm sorry for that, but let's say in general, I take 4 hours for doing something like this, for doing this. But just to give you the basic idea, right? So the basic idea was we have the statement of Floquet theorem. Floquet theorem tells us that I can actually solve the problem by solving a eigenvalue equation, which has the structure of a time-independent eigenvalue equation, right? Just on a larger space, on the space of the L2 functions with periodic time dependence, right? Then the eigenstates have themselves periodic time dependence, hence I can represent them as Fourier series. I can plug this Fourier series in the Floquet eigenvalue equation. From this plugging in of the Fourier series into the Floquet eigenvalue equation, I get this matrix representation of the Floquet Hamiltonian. From this, I get the eigenvalues and the Floquet eigenstates, and from this, I get solutions for arbitrary initial condition under an arbitrary periodic Hamiltonian. This ends the lecture. Longer, a little more detailed. Yes. you would like to. I would like to. I will send it to you. And also on the grid, I put my the grids here, right? So if I don't put it, I don't have to write in one slide. I'm not very happy that you must have it. Yes, I will also. I will put it in the. It's not. Yes, yes. I told you. Not all, but some are they also do it, right? We further. But I mean, we have to do this. That's what it is. Probably, right? So either, I mean, this part of the relation is happening. This the one thing is that the coupling terms are always identical. I'm not sure. Oh. And, or can you just wait? Then we.
Pues, a ver, más tarde,
Perché proprio il bello, che sia proprio il bello.